Alright, hell yeah. So we're going to use integration, triple integrals to find volume. Now, I got this problem from Houston Math Prep YouTube channel, volume by slicing. Now, this channel gets it done in 12 minutes and 36 seconds. So, we're probably going to spend a couple hours on this. If, hopefully maybe less, but maybe more. You never know. So, and what we have here is this shape going on. In the problem in that video, which I'll link in the description, they use a radius of 6 to negative 6. So we have, in this plane, we have a half circle, and that's going to define what these circles are. So, hey, this little circle is a little smaller. Right in the middle, this is kind of your biggest half circle, and we're going to add those slices up. So we're going to figure out what the area of that slice is, and then add all the slices all the way to here, and then add the slices all the way to there. So that's kind of the general gist, and so let's do it. And along the way, we're going to do a fairly rigorous process. So I'm going to use a coordinate system, kind of a 3D coordinate system. So we have the X, Y, and Z. And I'm going to put this half circle, so we're going to have a radius out here. I'm going to try to make it fairly big. Heck yeah. Cool. And then we're going to go all the way to there. Alright, so this is kind of the base of this shape that we're trying to find the area of. And then we're going to have half circles. Now, I'm just going to try to set it up. This is where you might want to, just really rough out a sketch and then keep improving on your sketch just to see if you can get everything in here. Because I'm gonna come here with this. So you can see that, hey, this is the radius. So I'm just going to call this R. So that point's R. This is going to be negative R. That means that this point right here in the Y direction is also R. You know what I mean? I could just come in here and say, hey, that's the radius. So it's just kind of nice to label things. We are going to be using equations of circles. So the most common equation of a circle is that, hey, this radius makes a hypotenuse. And then so we can drop down a horizontal. So that's going to be like maybe right there. And then we can drop down a horizontal in that direction. And so we just have to look at one of these triangles. But you can see, hey, this is a right triangle. We have the radius is a hypotenuse. So that comes up a lot in trigonometry, especially with angles. And in this case, we have our coordinate system. So like right here is a point along the x-axis. And so even though I think sometimes it gets confusing in math that we're calling this the x-axis, but it's just all points along that axis, you know what I mean? And so I think it might be confusing to be like, hey, this point is a distance x away. So, so we have this point's a distance x away, and then right here, this is a height of y. Okay, hell yeah. So you just have this relationship that Pythagorean theorem says that your hypotenuse squared is equal to, for a right triangle, your two sides squared, and then added together. So each of these sides squared, we're going to add them. That's going to equal the hypotenuse squared. Cool. So now let's start drawing that, that shape. We're going to have all these slices. So that's the next thing that we're going to draw in. And I don't have to get too crazy, but I kind of want to make it kind of tall as I can for a visual. Hey, so that looks pretty good. Now I'm going to go over one of the biggest misconceptions, and I'm even going to draw that shape again larger right here. You know what I mean? So let's get that shape going. And, you have some sort of axis there. This is your z-axis. This was the x-axis. And then this was your y-axis. You know what I mean? So this is parallel to the y. Anyway, I think you get it. So what I'm going to go over is kind of there's a misconception. I think this is one of the, so there's kind of, like, if I'm going to do a longer video, we're going to go over kind of the nitty-gritty of places you're just like, oh, I see it now I see it in a different way. So, thanks for showing me that. And let's just take always real simple examples. So let's say I have this line right here. It extends that way, but it's just y is equal to x. And sometimes you've seen this in calculus, is like you have this little strip right there. You know what I mean? And if this is the x-axis, this is the y-axis. This little, you know what I mean? We call that dx. It's just a small change in, you know, the x. So like, if this point right here was 1, you know what I mean? This is going to be, this point right there is 1 plus 0.0001 or whatever. You know what I mean? Just a very small change. Cool. And so what happens, though, is the misconception is like you start here in integration. You're just like, oh, if I have that slice, maybe I can add this slice next to it and that slice and this slice and this slice. And, you know what I mean? But this slice is a very different shape than that slice. So then the question is like, what gives? And then worse in calculus is maybe you'll have an equation that goes this way. Let's say this is 1 and 1, and then here's our line. And this line would be, and so this is at the basic. I mean, we're gonna be using this strategy in this problem, so we might as well start with the most basics. Is the things to not forget are Pythagorean's theorem, you know what I mean, for sure, and then just the general gist or the equation of a line. So if this is my y-axis, this is the x-axis. The equation of this line is going to have some sort of equation that's going to be y is equal to mx plus b. This is always a good one to start with. You know, we can visually see the slope is maybe -1. You know what I mean? Slope is rise over run. So if I have a run this way of 1, I went down 1. Cool. So we'd have y is equal to -x plus b. Maybe I don't know what the b is, but you know, I mean, just from general gist, it's the y-intercept. And even if you don't know that, it'd be more rigorous to be like, well, how do I solve for that? If this is the equation of a line, how do I get that little thing? Especially if I have a line that's, you know, I don't know where it's going through the y-axis. You know what I mean? So what we do is we just take a y value and an x value. So just one of these points, like a point, and let's take this point, you know what I mean? Even though, you know, this point right here is going to have is going to be 1, 0. So we're going to be over in the x-axis 1, is 0 in the y-axis, and we're going to throw this point into this equation. Now this point also is on this line, and so this is going to be 0, 1, x, y. Now these 2 points should, I guess, you know, I mean, satisfy this equation. And so I can throw in either of these 2 points to solve for b. So let's do this one. So we have y is 0. So we have 0 is equal to, and then we have -x. That's going to be -1 plus b. And then just bring this to the other side. We have 1 is equal to b. And hell yeah. So now we know that our y-intercept is 1. We have, and our slope is -1. So our equation for this line is y is equal to -x plus 1. Now, the reason why I kind of like slow roll something like that is because you're going to get something just a little more technical. And you still want to be able to, you know what I mean, kind of plow your way through effectively. All right, but the reason I did this right here is because we're going to do something different. You know what I mean? It happens less often in textbooks just because we're not used to it. But, you know what I mean, maybe we're going to take a slice sideways. So that's what we're going to do for this video. We're going to take, so if I take that little shape, I'm just going to put it right here. We're going to take a slice this way, and I'm going to take that same little shape, and then we're going to take a slice this way. And we're going to kind of compare what happens. And especially, this is a really good thing to do with a problem that involves circular arcs. Because what happens is that we can get an equation, you know, equation of a circle. And even if you don't know it, like it would be like, you know, kind of the common equation for a circle. And let's do the arc like this. You know, we have a radius, we have our y-axis and x-axis. See, because even right here, You know what I mean? Our axes are all different labels. So this half circle is in the vertical parts in the z-axis, the horizontal parts in the y-axis. And it's just when we work with math and equations, you know what I mean? Mainly we start with this. In 2 dimensions, we start with the x-axis and the y-axis, like this. And then so let's dive into that, and then we'll come back to this, because this will kind of explain, like, hey, we're gonna how do we add slices horizontally? How do we add slices vertically? And same thing happens here. Is like this slice, when we add it, is going to be different than the addition of that slice. So we're going to start adding slices from there to there, and these slices are going to be different. The foreshadow is, like, typically when you hear integration, someone's like, hey, what's integration? It's area under the curve. You hear that a lot. But that's why I'm spending so much time slow rolling this process, because like what we're going to do is not take a line. We're going to take a little segment that we're going to call, so if this is my y-axis, this is my x-axis. This little segment is a little change in y. You know what I mean? So, like, we don't have this yet. You know, that's the first integral. The first integral is the equation of a line. You know what I mean? So that's what we're going to show. And at its most simple, if it's a definite integral, you know, we're going to talk about that too. It's the length of that line. So if I try to solve for, if I come up with an integral for this, hey, I get the length of that line. That's it. You know what I mean? But if the length of that line is an equation, hey, then I can know the length of this line. I can know the length of that line. So that's kind of what's happening. Cool. All right, so for a circle, if we have x is y-axis, x-axis, we want to play that same game of like, hey, this is the radius, this is the radius, and if I draw if I draw a right triangle like this, I can say that this hypotenuse is the radius, and this point right here is a distance x that way, you know what I mean, and then up a distance y. And so here's the first thing that I'm going to go over, is that what do we have for just a generic equation? Let's go back to this equation, y is equal to x. If I say, and this is going to be 1 and 1, and then we'll go 2 and 2. So if I say x is 2, if I say x is 1, in this equation I'm going to put this number 1. So we're going to get y is equal to 1, and so what that means is, like, if I go over x, the equation is y is equal to 1. All right, hell yeah. So this is where we're going to go with that. If we have another equation that has a slope of 2. So this line is y is equal to 2x. Now in this, if I throw in x is equal to 1, hey, I get 2. So this equation, it says y is equal to 2. If I throw in x is 1, I get y is equal to 2. So what does this value represent? You know what I mean? I mean, it could represent a lot of things. Like it could be like, you know, I mean, in general, just it's always good to think like what equations are. Like the foreshadow is like in calculus, we're going to say this is a height. You know what I mean? Hey, it's 2. But like, what's another way to look at this equation? Y is equal to 2x. This comes a lot in especially in the sporting good, you know, business. Like, you know what I mean? Places like Dick's Sporting Goods or something like that. They're buying stuff at, like, let's say they buy a baseball glove and it cost them $50. You know what I mean? And guess what they can sell it for? They can sell it for $100. Cool. So that's going to this equation might represent that. It's just like, hey, whatever we bought something for out of the catalog, you know, from our retailers or from wholesale, like we have to price it using this equation. So y would be the price. So this X is going to be the cost of the inventory they bought from the wholesaler. So they bought something for $50. What are we going to charge for it? Well, we're going to use this equation. We're going to take that $50, multiply by 2, and we get $100. You know what I mean? And I think this is the realm that a lot of people, this is the realm that you start using equations. You know what I mean? You don't really think of equations as having a dimension. And so that's why I'm kind of slow rolling this process, is because this equation, y is equal to 2x, can represent the height, and visually it does. You know what I mean? On your calculator, when you graph this out or whatever, like what you get is this line. That is what you're getting. If I say y is equal to 2x and I put x is equal to 1, you know what I mean? So I get y is equal to 2 times 1. I get y is equal to 2. I don't get this line horizontally. You know what I mean? I get this line vertically. So that is the line that I get. All right, hell yeah. So let's see how that is related to this. You know what I mean? If we're wanting an equation, so if I use that, not even analogy, it's just what an equation is when we have y is equal to x. So for this, I'm going to try to get y is equal to something something x. In here, it's going to look like this, square root, x squared or something. So this is the equation of a circle. Like how do we relate x, y, and r? Well, we relate it with Pythagorean's theorem. And so, anytime that you get an equation that involves one or two things, you know what I mean? Hey, you can rearrange this thing. Well, there's 3 variables, so we can arrange this thing 3 ways. You know what I mean? So let's solve for y. You know what I mean? So we're going to get the x to the other side. And in today's video, we're going to work on also being okay with hey, I want to solve for y, and even though it's going to be on this side of the equation. You know what I mean? Sometimes it's useful to be like, nah, I can't handle that. Like the first step that I'm going to do is x squared plus y squared is equal to r squared. You know what I mean? It's comfortable. I'm just going to take this equation and then flip it. You know what I mean? It means the same thing. And now I can be like, okay, now I'm going to subtract this x over there. So we have x squared is equal to y squared minus x squared. So for this one, I'm going to do it this way just because, yeah, it's visually easier. And now I can take the square root of this side, square root of that side. So I have y is equal to the square root of r squared minus x squared. And even here, I guess we did a square root. Like I'm just not on point on this to see hey, if you do that, hey, we get 2 solutions. A y is equal to positive and a y is equal to negative. Cool. But for a half circle, we're going to see that the equation is just y is equal to r squared minus x squared. So that's the other part of the game, is to not lose touch of what these equations mean. So so that's the next thing I'm going to go over right now. Because I think the easiest thing to do with this Pythagorean's theorem is just solve for the hypotenuse. Like, isn't the hypotenuse just the square root of x squared plus y squared? Like, this equation gets drilled into you, and, we just kind of know it. And then visually, maybe you can see it. You know what I mean? So if I see, this squared plus this squared square root, I get a hypotenuse. And in this, hey, I get two components that are getting squared and then added. So this number has to be bigger than each of the components. You know what I mean? If I just had x squared plus 0 squared, well, then it would be equal to the component. And so that's a property of triangles, which will come up in this video as well. I can have a right triangle like this with a radius of r. This is my x and y. I can have just a right triangle like this. Still a triangle, maybe it's just imperceivable. But then, this is the radius. It looks like x is equal to r and y is equal to 0. So never forget about that one. Same thing with the vertical one. You know what I mean? I can have a, just hardly any sort of angle here. And then I have a y and then an x. And I can say, hey, maybe y is equal to the radius. And this x is basically 0. So I just have a vertical line. Alright, hell yeah. So then the other important thing to do is to actually throw in a value and see if that's what we get. You know what I mean? Is this representative of height? So for this one, I don't know. I mean, this is where knowing a little bit of trigonometry helps. Let's say the radius is 1, and I don't, you know what I mean, working with the unit circle I think sucks. I think you lose touch of reality with a radius of 1, because you're just like, well, then everything is kind of fractions. I don't know, it might make sense to do 100. And so let's do that. You know what I mean? Let's say the radius is 100, and this is the other thing with, I need to get hella more paper. Alright, mainly my videos are just kind of talking through the concept. Sorry if the drawings get kind of small, but I think these note cards will come in kind of handy, where we can write out these, I don't even know where the hell I was. We were talking about this height. Oh yeah. So yeah, the unit circle absolutely sucks. You know what I mean? It's a radius of 1. It's confusing. But what we have basically is you have a circle, you have your x. I should draw that hella better. And we're going to do that same thing. We're going to draw that hypotenuse in. This is the radius. This radius is also r, but we're going to drop that down. And then we have, you know, this point is an xy point. And it has a distance x this way, a distance y up. And so our whole objective is to get that equation for y. And then what do we know about a right triangle? This is kind of what I talk about right triangles. If you know, you set a value for x and you set a value for y, and you know your hypotenuse, well, you know what I mean, you know what this angle is. Cool. And then we can use the concept of like all sines. Like, let's start with just sine and cosine. Sine of an angle, cosine of an angle, they're percentages. They're given whatever dimensions we put on x, y, and r. And in this case, we just need to know, like, the hypotenuse in one of these sides is what we're saying. And this is a good thing to do visually, always. You know, if you draw a right triangle, just kind of visualize your hypotenuse and then visualize what the percentage of these sides are. So one thing that I always do is just take the hypotenuse, divide it into 2, and that's kind of the first check on reality. Is one of these sides less than that length or half the hypotenuse? And it's like, no. All these components are more than 50, and you can even say that. These components are more than 50% of the hypotenuse. I mean, just kind of visually, you know, maybe this looks like 60%. You know, maybe this looks like 80%. And that gives you your 3, 4, 5 triangle. You know what I mean? That would be an exact measurement. That's the only one that kind of comes out nice is the 3, 4, 5. And that means that this component is 60% of your hypotenuse. This is 80% of the hypotenuse. Okay, so but yeah, and then if we set that radius equals to 100, you're like, oh, okay, so if this dimension is 100, now we actually have some, you know, dimension to it. Hey, this is going to be 60, because it's 60% of 100, hell yeah, and this is going to be 80, that's going to be 80% of 100. So this length is 80, this length is 60, and booyah. And what were we trying to say? We were saying, hey, the name of the game is to figure out what height that is. And so if we you know, if we have that shape and the radius is 100, hey, this y is going to be 80. All right, and then let's go just back to this equation and see if we can throw that in, because this equation, we're not going to be using angles until we use the trigonometric, until we get to the fact that we can't integrate this. And the reason why, so this is good to go over even right now, we have r squared is minus x squared. Now, if you had to differentiate this, you know what I mean, and what would we should even talk about that, because integration is just the opposite of differentiation. And so how you would differentiate this equation right here is you would say, hey, what's the change in this equation if I change my x value? And so if this equation represents this height given this x value, well, let's try it out. So if I if I change my x value from here to here, hey, does my y value like change a decent amount? And hell yeah, it does. How about and I change my x value just the same amount from here to there, does my y value change? Yeah, it's even about the same amount. You know, it dropped to there, it dropped to there. But now if I change my my x value that same amount, whoa, it actually drops way down here. And had I started right here and I had this height, and I changed my x value just right here, hey, did my y value change at all? No, not really. You know what I mean? So when I take the derivative of this function and then get some other function, you know what I mean, that has x in it, it should represent the fact that was it supposed to represent? Yeah, it should represent that if your x value is right there, hey, there's going to be no change. You know what I mean? So, because this derivative says, hey, what's the change in this height when my x value is like right here? It was like there is no change, hardly any change, hardly any change, a little bit more change. So by the time I actually throw in, and now we're going to go back to the unit circle, it was like, hey, if this is a distance of 1, by the time I actually get to about 0.5, hell yeah, now we got some change. And then if I get to a value of like 0.9, you know what I mean, whoa, we're going to get a ton of change. You know, so that's what that equation would represent. And booyah. And this is smart to do. Like anytime you're going through a problem, and you know, if you have just like 10 hours to waste or spare or to like keep the learning process going, you know what I mean, just ask yourself a question, and it's just like, well, what is a derivative? You know what I mean? And then you can just talk your way through it. But when it comes to derivatives, you can always take a derivative. You know what I mean? So we could do that easily just like right now. You know what I mean? Just using the properties. It's hella difficult to take integrals. And because what happens is you know what I mean? If you do a u substitution, hey, this u is going to be like an x squared. And then you're going to have to, you know, this, if we do the integral of this with a dx, you know what I mean? So the integral of this equation, dx, and then we have, you know, we set this as our u. You know what I mean? We'll have u to the, you know, our du will be 2x. And if we do the change in this, you know, substitution, du dx. So it's like, hey, if I have this as my equation, you know, same thing is if, hey, this is now my equation where I have x squared. What this is, you know, you could also say, hey, this is height. At x equals 1, you know, hey, my height is 1. At x equals 2, hey, my height is 4. You know what I mean? That's just this just basic equation. But when we take the derivative of it, we get du dx. So the change in this, no change here, and then quite a bit of change. And oh, actually, the change is the same amount all the way through. Oh, that's interesting. Now, I guess the change is not constant, but it is linear. It's getting, yes, it's increasing. There's not much change here, more change. Yeah, hell yeah, there's more change. But it's a linear increasing change. So we get this, and your u substitution would, you know what I mean? You have this integration where you have this equation dx, and you're integrating it. And you substitute this value for u. And then you get this du is 2x, dx, get the x dx up there. I can sub this dx right into there, but hey, this 2x doesn't go away. You know what I mean? And so, you know, I can't integrate it with this new variable u because that I still have this x to contend with. And so that's kind of the bummer about integration. Is if I have an x squared in here and I have this u, I would probably have to have an x out here. You know what I mean? To sub this du perfectly into that equation. But the opposite, hell yeah, we can take the derivative of this, and I guess we will. It's just good practice, I guess. So we're going to go dy dx, and yeah, I mean, essentially, we're going to use the u substitution. So we're going to say, hey, this is... Now, I'm just going to do this fastest way possible. So, hell yeah, I kind of see this as u substitution. So we have a 1/2 power. I'm going to bring that 1/2 power down, just write everything in here, and then lower the power. So this becomes, it goes from 1/2 to negative 1/2. Sweet. And then we have to take the derivative of the inside. Derivative of this is 0, but the derivative of this, bring down the 2, so we got negative 2. That goes to x. So hell yes, this is what we have. So we would have negative x upstairs square root r squared minus x squared. And let's see if this jives. If that is the derivative of that equation, does that make sense? When we have x is 0, or just really, if x is a small number. So if x is 0, we just have r. So we would have downstairs, we would just have r. And we would have, approximately r. And then upstairs, we would just have just a very small number, close to 0. So let's just say it's 0.001. Because if we take 0.001, 001 and we square it, hell yeah, now we're just subtracting 10 to the negative 6. I mean, we're subtracting, this was 1,000th, now we're subtracting 1,000,000th, you know what I mean? And what the hell is 1,000,000th? It's microscopic, you know what I mean? So we still have, basically this is approximately r downstairs, and then we have 1,000th, that's going to be the same thing as 1,000th r. Divided by r. If r is 1, you know what I mean? Hey, we have our change right here is 1,000th. Compared to if we go to the other end of the spectrum, or just even go half. Let's say r is 1, the radius, we're going to go to a half, so we're going to have 1 squared minus a half squared. And so that's going to be 1 minus a quarter. That's going to be 3/4 downstairs. We're going to take the square root of that. I didn't really want to do that one. All right, but the other hot values on a triangle is when theta is equal to, like, let's say this is 30 degrees, so we're way out. This is going to be 0.866. It's a good one to remember. If this is 1 and this is 30 degrees, hey, this is 1/2. Everyone remembers that. But this, as a decimal, is a very good one to memorize, 0.866, because like literally the next number is 0, and then I think it's like a 2. And then it's also good to know where this comes from, because if you double it, you get 1.7, and we can even do this. You know what I mean? We're going to get 1.6. We double that. Double this 6. We get that. So we get these 12. So we get 2, 3, 7, 1. Always good to also, you know what I mean? A good one to double is 3.14. Double that, hell yeah. You get 6.28. That comes up a lot. That's 2 pi. So it's also good to kind of see where that number comes from. But hell yeah, just to even spot. And then the other number is like what the number, obviously we know 6.28, we know 3.14. But if you half this, you're going to have 1.5 and then subtract 0.07. I'm sorry. You're going to have 1.5, but then you're also going to have half of 0.1. Half of this 14 is 7, so it's 700. So we have 1.57, and this is also, I think there's probably like another 1 there. You know what I mean? What's half of pi? Pi divided by 2 is 1.57. So yeah, and there's a 0 there. So I'm just bringing these up. There's certain decimals that are worth, I love the decimals that are like for sure worth memorizing to 3 decimal places. This one too. So what this number is, so this should ring bells. You know what I mean? If it doesn't, definitely 1.4142 should ring bells. And 1.732. So the square root of 3, this is the square root of 3. So that means that this is the square root of 3 divided by 2. And that's going to be useful because we can throw it in this equation and get kind of an idea of how much that slope is going to change because we just did the derivative. Yeah, and this one also, it's got a 0 after it. So just really clutch numbers to know to 3 decimal places. Because if we divide that by 2, hell yeah, you get a 0 after that. So, and hell yeah, 1.57 also has a 0 after that. So just real accurate. This one's perfect to 2 decimal places. You know, if you're doing 3.14, good enough. 6.28, good enough. 1.57. And the reason these are good enough to 2 decimal places is because, hell yeah, what's 2 pi? You know what I mean? You have a pretty low number after it. You have a, 3.142. Yeah, that's a little bit better. Is that right? What is pi? Yeah, 3.1415. Yeah, so even, just a 1 after it. And then if you half that, hell yeah, that goes to 1.570. All right, booyah. So we're going to throw that into this equation and just kind of use that value. So our x is going to be 0.866 and into this derivative. So we have this y, this derivative of y. You can write it like this. That's going to be negative x divided by r squared minus x squared. And, you could just throw in 0.866 like that. Square root r is going to be 1. We got 1 squared minus 0.866 squared. But obviously, you're not going to do that. You're going to use this as, hey, this is square root 3 divided by 2. But I think fractions, and especially fractions with roots, are just atrocious. It seems like they don't mean nothing. You know what I mean? So it's just good to see where that decimal equivalent. And hell yeah, square root 3 divided by 2 is 86%. That is the most important take-home message right there, that this length is 86.6% of this hypotenuse. And for a unit circle, if this is 1, this is 0.866. All right, hell yeah. So let's throw it into our equation. We're going to have the square root of 3 divided by 2. Booyah. And then we have 1 squared minus square root 3 divided by 2. This is going to get squared. So now we're going to get something halfway nicer. Maybe not, though. You never know. But yeah, this is going to be 3 divided by 4 now. Cool. And then we got 1 minus 3 divided by 4. That's going to be 1/4. We got the square root of that. That's the square root 1, square root 4. And then this bottom is going to be 1/2. Okay, hell yeah. So, dividing by a half, same thing as multiplying by 2. And we get negative square root 3 divided by 2 times 2 divided by 1. So this just becomes, our slope is changing. It's getting negatively steeper by a factor of 1.732. So hell yeah. So like right there, it's getting steeper. And then so, you know what I mean? Hey, the slope is 0 here. So at 45 degrees, hey, the slope is 1. At 30 degrees, hey, the slope is about 2. And then the slope would be infinite as x approaches r. And is that what we would see? So if this is also r, we would have r squared minus r squared. This would be 0 in the denominator. And hell yeah, this would make this negative infinity. So we would have a negative, infinitely steep negative slope. All right, hell yeah. So that was a worthwhile tangent just to show you that, you know what I mean? And I think that's where, yeah, if you're doing derivatives, life is easy. You know, even if they get complex, you can probably follow the logic a lot easier. Where integrals, hell no. You know what I mean? You have to have an equation that when you differentiate it, you get this. And the only way you're going to get an equation that when you differentiate that is if you have x, you know what I mean? If you have something like this. No, I'm sorry. I mean, my game isn't very good. Or even if, yeah, I don't even know what that would look like. But if we started with x is equal to the square root of r squared minus x squared, hell yeah, we could use substitution. We would get an equation. And then, yeah, it's always good to, hey, take that integrated equation and then differentiate it. You know, that's a step that I kind of forget to do. And you'll get right back to that equation. All right, hell yeah. So now we're going to kind of go back to our problem. And so we have an equation for the height of that line. And if our x value is here, this is the height of that line. If our x value is all the way at the radius, we have 0 height. And so this is the equation for the height of that line. Now let's take a look at when we throw in a positive x value. Because this is squared, we're going to take that value. If it's positive, let's say it's positive 1, we're going to square it. That gives us 1. And then we're going to subtract it from this side. So if this radius is 1, it's going to be 1 minus 1, and we'd be at 0. So if I'm out here at a radius of 1, or at a distance 1, that is the radius, so that height of that equation is 0. Now if I come over here, let's do the same thing over here. If I do a negative value, let's just say I do negative, you can just think like negative a half, but anyway, it's just going to be a negative a number. We're going to square that. This number is now going to be positive, and it might be positive a quarter. So then we're going to have 1 minus a quarter. So we would have we would have 1 minus a quarter to be 3/4, and then the square root. It's always good to do that. Square root of 3/4. If that seems difficult, just break it up into components. Square root of 3, square root of 4. Hey, square root of 4 is 2. That's the square root of 3 divided by 2. And again, hey, that number pops up. That's going to be 1.732 divided by 2. That's going to be 0.866. That's 86, basically 86%. And so if I come over a distance x, which is half, yeah, I would just expect, but sometimes you lose touch of like the basic trigonometries, especially when you're using a circle. I don't know. There's just something about the unit circle that I don't like. It seems like I would just rather do the trigonometry with right triangles, but the fact that you have this curve in here, and then, I have to kind of get better at that. But hell yeah. So the height of this is going to be 0.866, and that's what we would expect. And we can just do it visually. If this radius is 1, look at this. We divide this radius, this hypotenuse, up in half, and we see, hey, this is definitely bigger than half. Break it up into 3/4, and yeah, I can maybe see that this is just bigger than 3/4. Yeah, this is going to be 0.866. And so, but then the other thing here, though, is that what we did is we threw in a negative value of x, and we got a positive value for y. So this equation holds for positive values of x and negative values of x. And but it does not give us anything down here. It is only a half a circle. And so what we're going to find is that this equation works very well if we find this height. If we find the height at this point of x, or over here, or right there, all across this, and that's kind of what we're going to be doing for integration. We're going to be taking that height and then turning it into a little slice and then adding those slices. But we for sure need to know the height of all those slices. And this equation does that. But if we do it vertically, I was saying that if you do integration, there's two different, there's two different starting points. You can come over here on our little half circle, and you can do a vertical, and that's what we just did. That's what we got done doing a little vertical distance, calling it dy, and then integrating that dy. And the limits on here, well, hey, this is an equation. This is y is equal to 0. Hey, what's the equation for this? It's r squared minus x squared. And this equation should be pretty fast to chisel out, because, hey, you have that radius, you have x and y, and we're interested in the y value. We're interested in the, and I guess I didn't really mention this, but yeah, if you have Pythagorean's theorem and you're trying to solve, well, we already solved for y, but it's going to be the hypotenuse squared minus the side squared. And in that process, you're going to get a smaller number always, unless you have 0 angle or 90 degrees. That's when one of your sides is equal to your hypotenuse. All other, just any normal right triangle, any triangle that's visually a triangle, right triangle, the side will always be less than the hypotenuse. And that is very evident in this equation. You know what I mean? So just visually, it's a good one to be like, if you're looking at this and you're seeing Greek, you know what I mean? That's one step in the right direction that you're like, oh, I see that bigger number, the hypotenuse, being subtracted by the smaller number on the side. And sure, these are squared. But that is going to give me a bigger number minus a smaller number. In the end is also going to give me a number that is smaller than the hypotenuse. So that's kind of visually what I see when I see this. And compared to having any two numbers, a squared plus b squared, well, now I know this visually represents a hypotenuse. You know what I mean? But if I see, and you can choose whatever letters. You could say e squared minus d squared. You know, if I see this, I know that this is a component of a right triangle where this is my hypotenuse and this is another side. So that is a visual representation of what that represents. And just like this was an equation of like how to price sporting goods, yeah, maybe this is an equation that has no that is not based on geometry. You know, it's an equation that's used for something else in the known universe. But it has a physical, you know what I mean? But if you use it to show geometry, like it's very obvious, you know what I mean? And I guess that is one of the only cool things about calculus is you take these equations that you've used in algebra and you finally get to visualize them in 2 dimensions. You know what I mean? I guess a line is 1 dimension, area 2 dimensions, and volume in 3 dimensions. So it's kind of cool. All right, and then, yeah, just even saying that's the trippy, again, the trippiest part about calculus is that a lot of calculus will already start with this slice. And I don't think you're doing yourself a service. That's why I'm always trying to start a calculus problem with just a tiny point, you know what I mean, and then making that point have some sort of differential, in this case dy, differential height, and then so we can do it with a differential width. I can say that, hey, this is a little width dx, and I want to sum the widths from here to there. And that will, and yes, and if we do that with the integral symbols, we'll have the integral of dx, where we have our limits of integration from some sort of x point to y point. Now, if this was if we wanted to simplify this problem, what we would do is just do a box where, hey, this is my x, this is my y, and I can say that this line is x equals 0. Because if I have a point up here where it has x, y, where y is, let's say, 1, well, guess what x is? It's 0. And any point along this line, x is going to be 0. So that's where we can say this line is x equals 0. Same thing over here. This is an xy point. The y value is 1. Guess what? The x value is 1. Same thing down here. xy, the x value, the y value is 0, and the x value is 1. So any point along this line, the x value is always going to be 1. No matter what the y value is. Y could be negative 3 down here. The x value is still 1. 1, negative 3. All right. And where were we going with this? We were showing... Oh yeah, we were trying to do this. We're trying to take a little... So we're trying to get... start differentiation with just a small little segment. So this is going to be a small dx segment, a distance x away. And we're going to integrate. We're going to try to add these segments up. But we need to know where we're adding and like where are limits of integration. Because we're not adding that segment. We're not adding that segment. So we're starting here and then moving to there. Now for something like this, let's say this is like a cube of 1 and 1, and we're starting at a height of 1/2. And I just want to know the length of this line. Let's see how we would do it. Well, it will give us the length. That's literally what the summation of all these little segments are. And so when we have the limits of integration from 0 to 1, x is 0, x is 1, and we use our I don't know if this is even the power rule of integration. I guess it is if you're saying that this is the integration of x to the 0 power dx. Sometimes I like to do that because you're just like, well, why isn't... I would know what the integration of x dx from the power rule, because this has... But even there, you'd want to throw the power x to the 1, and the integration of this is x to the 1 plus 1 divided by 1 plus 1, and that's going to be x squared divided by 2. So if you do have just dx, you can always throw an x to the 0 in here, and when we integrate, it's going to be x to the 0 plus 1 divided by 0 plus 1. So that is that is the power rule of integration, and you're going to have a constant. Now on here you can put the constant, well, and then you evaluate it. So yeah, and you would have a constant, I guess, in 1 and 0, and because when you evaluate your limits of integration, or let's clean this up. So this is x to the 1 divided by 1. So it's just x evaluated 1 to 0, and we get 1 minus 0. You know what I mean? And if we had constants of integration, if we kept that on here, we would have, throw in 1 for x, we would have 1 plus c minus 0 plus c. So this would be 1 plus c minus 0 minus c. This plus c cancels that minus c, and your constant of integration for that's just visual representation of how that drops out. All right, so in this integral, the length of this line is 1, and it's just the length is 1, and it's also the equation of this line. And the equation of this line, because we just integrated, let's I'm kind of bad at this. This isn't going to be the crispiest, but it's because we're bad at tipping this way. You know what I mean? Like, we integrated, and so I said if you integrate, so it was just fine if we did it vertically. So let's do this. Let's do this one vertically to show kind of the difference. So we have x, y. This is the distance 1 and 1. I'm going to take a little vertical slice, and this is going to be in the y direction, a distance y from the origin. And then I'm going to add that slice and that slice and that slice. I'm not going to add that slice. I'm not going to add that slice. So I do have limits of integration. So I have dy. And then my limits of integration have to be in terms of y. And so this is an equation of a line that's y is equal to 0. It's much easier because we're so ingrained that horizontal lines are constants where y is equal to a constant. No different with vertical lines being x is equal to a constant, but it's just easier to see the y equals. So this is y equals 1. So that's the equation. So our limits of integration, we're going to sum all these little chunks from here to there, and so we have 0 to 1. And same thing. When we integrate this, we're going to have y evaluated 0 to 1. You could throw in the constant, but like I said, we're going to do, because what is this called? Like where you actually, is it called a definite integral? I don't know my terminology, but when you're actually trying to find the length of this line, integrating gives you, yeah, and we should probably talk about it. I should probably pause and then refresh, but yeah, I guess that's a place where I'm not super confident talking about. But anyway, so when we, the limits on this is just going to be 1 minus 0, and so that's going to be 1. Now, cool. Now, what does that represent? This represents the height of that line. Well, didn't we say just a general equation? If I have this y is equal to 1, and I choose any x value, doesn't x, when I choose x is equal to 1 in this equation, which isn't a function of x, but any value of x, chisels out this y is equal to 1, and we've been talking about how that is a height. So going back over here, just because, so this was differentiating this little dy, and what we get is an equation of a line that's and once we integrated this, we get 1. Like 1 what? Well, this is a function y is equal to 1. After integrating this is the same thing as an equation y is equal to 1, where the height is 1 at any given value of x. And I think sometimes, kind of like when a problem gets too easy, it gets a little bit kind of harder to see. So let's do kind of one of my favorites. Is we're going to take the equation 2x and then the equation x. So this is y is equal to 2x, and this is y is equal to x. What we're wanting to find, and we're gonna do our little slice. So there you go. So there's our little slice. There's our little dy, and then we have and we want to know, like 1. If I'm just choosing, and I guess the other thing that I haven't specified is like, hey, I just chose this, but I did choose it at an arbitrary value of x. I could come up here and it's just like, well, you did choose this little dy at some x distance, you know what I mean? So we can keep that in mind. But this integral of dy, setting my limits of integration, what is this giving me? Well, it's giving me the height of this line. And the height of that line is going to be an equation. So let's do this one. So our limits of integration start at y is equal to x. And then they go up to this line, which is y is equal to 2x. And then so when we integrate this, we're going to have y evaluated at 2x, x to 2x. So we're going to have 2x minus x. That's just going to be x. So what does this give us? Again, this is giving us height. This is the height, and it's in the form of an equation. So we were integrating this direction, so we would have with dy. So this is the equation y is equal to x. So if I have y is equal to x, this that's the height of that little section right there. The height of this section is so if I go to that same location, that section height is the same as that section height. And because we just kind of chose whatever arbitrary value, is just like, hey, now I know the height right there. Given this value of x, I know the height of that line because it's this equation. So that's where so yeah, let's see if I can answer my own question, because I'm just curious about that one. So I'm going to go 1, 2, 3, 4, 1, 2, 3, 4. So I have this y is equal to x, and then I have y is equal to 2x. So this line. And I'm curious of what the, like, let's say I just want to know the height of that line right there. That's all I'm interested in. So I guess we're going to draw a picture again. 1, 2, 3, 4. 1, 2, 3, 4. And so I'm going to come in here at this location of x. I'm going to make my little dy length. You know what I mean? So I have, and I'm going to integrate, which means I'm going to add up all these little segments from here to there. And so I have y is equal to, this is y is equal to x, this is y is equal to 2x. And, oh yeah, but what I wanted to do is just like, well, don't I know, if I'm just trying to find the height of this line in particular, can't I just say, like, hey, don't I know what the height, don't I know this point? This point's going to be 2, 2. And this point right here is going to be 2, 4. So, you know what I mean? I actually know the height. So this would be like saying, hey, if I just want to know the height of that line, I can even just kind of throw an equation in here that's y is equal to 2, and an equation here y is equal to 4. And then so my limits of integration become y is equal to 2, y is equal to 4. Now this specifically is going to give me the height of that line. But that's it. It's not going to give me the height of that line. You know what I mean? So, so that's the difference between setting my limits is like, well, I'm just going to set this arbitrarily. It could be this segment, and I want to know that height. And so if I'm going to vary the location of this dy, you know, this way, then yeah, so then the integration process is giving me the equation of that line. And it's just kind of fascinating for 2x and x that the equation that you get is just y is equal to x. And so this height at x equals 2, that height is that height right there. So if this height right here is the same as this height with this equation. So this is the height, x equals 2, so 2 is the height when x equals 2. All right, hell yeah. So I think we've thoroughly gone over this, you know, definitely in the vertical direction. And then in the horizontal direction, yes, if I sum all these points, but I want to vary this location, you know what I mean? If I wanted to sum those points, then I'm going to get an equation of this line. And there's no difference than tipping that vertically and saying, like, if I got the equation of this line, this is going to be a y is equal to something something x. That means that this equation right here is going to be x is equal to something something y. You know what I mean? It's x is a function of y in some form. And I just think in calculus, it's harder to see a horizontal line as an equation when we're so used to vertical lines. Sweet. All right, so now we can kind of get back to the problem. And especially the fact, because that's what I wanted to do with this problem right off the bat is like, hey, let's do it the harder way, or maybe not the harder way, just like the way that I might do it, just because it's just like, hey, I might draw this little segment in here and say that it's this is the y-axis, this is just a little dy. And then what I want to do is, let's get more cards. I want to integrate dy, but now I need to know what my limits of integration are. And now this is a little bit of a disservice because we have to kind of throw out the idea that I've been using this xy for this circle and saying, hey, this was the equation y equals r squared minus x squared square root. But because we went over this and saw that this is the hypotenuse, this is subtracting one of the sides, it must be the other side. But in this, our y was our vertical direction, our x was our horizontal direction. But on this little slice, this little half circle, we have y as our horizontal direction and z is our vertical direction. So let's draw this half circle in where we have y. And then the other thing that's going to be a bugger on this is this isn't, it's not centered. You know what I mean? The half circle is not centered at the origin. But we can still start. So here's my tricks of the trade. I can still say, well, I'm just going to pretend that it's at the origin. You know, maybe just kind of come down here. And this is where it's kind of useful to like. But anyway, this is all I used for this one. I said, hey, I know that this is, well, and then check this out. So for this problem, back to this, you know, back to this problem, I guess, that this is our radius. I'm going to have this variable r. But this circle has a new radius. And, you know, it'll change. You know what I mean? If I take the slice there, that radius is going to be much smaller than this one. So that radius is going to be a function of something. And it's basically just where it is located along this circle. So if this half circle is located right here, well, then this radius is just half of that radius. So if I get this radius as a function of something, I can double check that, hey, when the x value is 0, this radius of this circle, and for this problem I just called it r naught. I don't like primes because what happens, I started with primes, but if you do primes and then you square it, I don't know, that just kind of gets in the way. So if I'm going to say this is a different radius, I'm just going to call it r naught. If I had a different one, I could call it rb, rc, rd, I don't know, you know what I mean? But just having something down here that's not just a little hash mark, but hell yeah. So we're going to call the radius of this circle r naught. And so we're going to play that same game as like, hey, this is r naught, this hypotenuse is r naught, we're going to drop this down. Now this height is z, it is in the z-axis, but I do have to call this dimension, I'm going to call it y naught. And just in the same vein, you know, just calling it a different variable. I know it's some sort of y direction, but it's not the actual y value to this problem. So if I say that this is a, you know, if this is my axis, zy, and sometimes it's difficult, you know what I mean? Sometimes it is better, it's easier just to go back to like an xy axis and be like, if I have a point over here, what is this point? It's xy. So then if I go to this axis, and this is zy, what is this point? Well, this is going to be yz. And just getting good at being like, okay, this is the y, and I need to look up what the hell the independent and dependent variable is. I don't want to guess because, yeah, I need to look that up tonight so I can use those terms. So does it make sense that just with an xy, is this the independent variable? I mean, does that make sense? Like, I swear you could go both ways with things sometimes with definitions, but you know what I mean, this is 0, 1, 2, it's not dependent on anything else. It is a number line that has equal numbers between it. It's an independent variable. That makes sense to me. But this variable right here, this is your height. Yeah, that's going to depend on this function that you chose. You know what I mean? So this height y is your dependent variable. It's dependent, but maybe I'm just saying it the total opposite. That's the garbage thing about definitions sometimes that are kind of closely related. All right, so back to this one. So this point right here has a y, which is all the way out to here. So this is my distance y. This is my distance z. And so, but we did want to clarify this y naught because we can use Pythagorean's theorem. It's just kind of fascinating that Pythagorean's theorem gives us the equation. So if I have, this is my hypotenuse and these are my two sides, I can say the hypotenuse squared is equal to one of these side squareds. I'm going to go y naught squared plus z squared. And then what I want is this equation. Just like here I wanted an equation y is equal to radius squared minus x squared. You know what I mean? Here I want something in the form of z is equal to the radius squared minus, and in this case it's y naught squared. So that's what we're going to get. So let's rearrange that and we'll get this. We're going to, so here's where I'm going to, yeah, I want to solve for z. Z's going to be over here the entire time and then we can flip them around. So let's subtract. So we're going to have r naught squared minus y naught squared is equal to z squared. And we're going to take the square root of both sides. This gives me z is equal to the square root of r naught squared minus y naught squared. Hell yeah. And if you need to, you know, I mean, you can flip it around. Don't have to. But it is good. We read left to right, so it is good to kind of clean that up. Okay. But this isn't the value of y that you would throw in. So then this is like I try not to let this stuff give me hiccups, but I don't know, you know what I mean? This happens in trigonometry all the time. It's just like, well, what is this distance y? Well, it's r naught plus y naught. You know, if I go r naught plus y naught, I get y. So if I see that first, if I see like r naught plus y naught, I'm just going to say that r naught plus y naught is y. Hey, I got this equation. Even if I couldn't see it as y is equal to r naught plus, you know what I mean? But there you go. So this, and this is a, like, because, and I guess how you would want it is like, hey, I have this equation that's in terms of y naught. And I need this in terms of y. And I just can't see that. I can't see. But it's good to also go back and be like, hey, how do I get this length in terms of here? Well, I would say it's y minus r naught. And this happens in trigonometry all the time, especially if you have a length that overtops especially other lengths. You know what I mean? This length right here is the big length minus the intermediate length. You know what I mean? So I can see that. So I could have said that y naught is equal to y minus r naught, just all in one go. But I think it was easier to say r naught plus y naught is equal to y, and then we're going to solve this for y naught. So y naught is equal to y minus r naught, getting this to the other side. And so those two are the same. So now I can throw this term y naught into here, and there we go. And I can even do this. I can go, you know, sometimes it is useful to do like an intermediate step before you plug something into an equation. So this is y naught squared. I just took this value squared. You could even do this, you know what I mean, just to get practice, be like, hey, what's negative y naught squared? Well, that's going to be negative y minus r naught squared. Okay, now I'm going to throw this value in for negative y naught squared. Cool. So this function z is r naught squared. Alright, hell yeah. So let's see if we can get more light. There we go. Alright, so this function is r naught squared minus, you know what I mean, or this term, you know what I mean. That was probably awkward to do it all the way to there. But hell yeah. This was y minus r naught. We're going to throw it into there. So we have minus parentheses y minus r naught, and we're going to square it. And that is our function. Cool. Okay, so, but we have to have a check on reality. So back to, let's see, yeah, back to, do I have any other pictures? Did I draw some more pictures of that? I guess just this one. So we have this, and we have an equation. Z is equal to, you know, just all that square root. So yeah, this is our equation for this line. And let's hash it out. If I throw in a value of, let's say I throw in a value of y that's equal to r naught. Okay, so it's going to be r naught minus r naught. That term goes away. And so this term is just r naught. Does that make sense? Is my height the radius? Hell yeah. So we're good to go there. Now if I make this term y bigger, you know what I mean? Now I have like this number is going to be bigger than this term. So I'm going to have a residual positive value. We're going to square it, and then we're going to take that and we're going to subtract it from the original radius. So if I come past this radius, I should expect a height that's lower than the radius of the circle, and I do, so that's check on reality. Now if I come less than the radius, if I say this is less than the radius, I'm going to have a number less minus a bigger number. So I'm going to get a negative number. We're going to square it. The negative is going to go away. And then we're going to subtract that from the radius, you know, squared. And so that still gives me a number that's smaller than the radius. So if I only come a y value over here, yes, my height is going to be smaller than the radius. That's a check on reality. Now for this equation, let's say I wanted to throw in a value of y and get, and I wanted this to be a full circle, and I wanted to get this height down here, like a negative height. Well, the only way to do that is by, so yeah, let's draw this out, is by taking this equation and doing this to it. Negative r naught squared minus y minus, you know what I mean? Just putting this negative in here, because if I said, hey, if this value of y gave me this height, but then I wanted this lower circle down here, and if I threw in the value of y in this equation, I would get this negative height. And that's going to be useful to know, because on this problem, because like right here, what we chose to do is we chose to take our circle and I might have misrepresented even this, because I want to do this. You know, it's the harder way to do it. But even right here, what we got was we took a little a little dz chunk, and well, we haven't even done that. But what we did is we got this, I guess, yeah. So back to here, if I chose to do this, you know what I mean, and I chose to take a little chunk this way that has a little dy. Sorry about that y right there. But we have a little dy, and I want to add all the y, these little segments from there to there. When we do that, we have to have these limits of integration in terms of y. So I just found this equation in terms of z. You know what I mean? It was the square root of r naught squared minus y naught squared. Cool. But my limits of integration are in terms of y. And so let's take a look at the simplest case where we just have, we know that this is our half circle, rxy, and then the equation of this is y is, and we can do this kind of fast now because it's just this height. The height of a right triangle, one of the sides, is the radius squared minus the other side squared. So you can really chisel that out. But if I come in here and say, hey, I want to take this little chunk this way, this would be a dx, a distance x away, and I want to integrate dx, and my limits of integration have to be in terms of x. So if I'm going to start at this point right here, I either need to know what that point is in terms of x as an actual number, and this point as an actual number. And if I had these as actual numbers, all that's going to give me is the length of this line, you know, just one line. But what I want is an equation where I want to know if I vary that height, I want to know the length of that line. So even that should spell like, well, what am I varying there after I integrate? I'm varying a y term. So I need to get this equation as x equals, you know, something y. And it's just really easy to do things as, you know, yx to get this. It's just, that's the most familiar thing we're able to do, is get a function in terms of y, represent it as a vertical height. And what's going to happen is that, well, we're going to solve this, and I'll show you. What's going to happen is that when we solve for x, it's just going to, when we solve this equation for x, it's actually going to give us this circle. You know what I mean? Where if we throw in a value for y up here, it's going to give us this length right there. But it's not going to give us that length over there. And well, we're going to find out that I need to take this equation. This is going to be x equals, you know, r squared minus y squared. I mean, we'll go through the algebraic process to do that. But you could just say, hey, what's this length x? You know what I mean? From this, I could be like, well, that length x is the radius squared minus y squared. We kind of talked about that, how it's the hypotenuse squared minus the other side squared. It has to be this, you know, square root that has to be this side. That's one of the things that I think would be very useful to have just on lockdown, because then in trig identity books, you can kind of see this and be like, oh yeah, that's the side where this is the hypotenuse and this is one of the other sides of the right triangle. But what happens is when I throw in a value of y, I get this this height. I get a positive x for my height. And if I throw in a negative value of y, that's going to square, so it's going to become that same positive value of y. We're going to subtract it from the hypotenuse, so we have positive value of y, squared, and that's going to if I come down here for a negative y, it's going to give me a positive x height. So, but in our problem, if this is my little slice, I need to add those slices. So the only way to add those slices is to get this equation. And so this equation is going to be x is equal to negative r squared minus y squared. So then if I come up here and throw in a positive value for y, we're going to square it. We're going to subtract it from the bigger number, the hypotenuse. The bigger number subtracted by a smaller number. This is a net positive, and then taking the square root. But in this negative makes it a negative. If this is my origin xy, this distance is the negative x direction. Cool. All right, hell yeah. So let's do that from scratch. So if I have this half circle, I'm going to take this little dx chunk. I want to add these slices up. I can easily get the fact that this is xy radius, and then this equation is y equals. And sometimes you have to start there. Hey, this is y equals r squared minus x squared. This is kind of the crawling before you walk. And now let's do the algebraic process to solve for x. So we're going to have y squared is equal to r squared minus x squared. I want to get the x over here, so we're going to have x squared is equal to r squared minus y squared. And then I'm going to take a square root of both sides. So x is the square root of r squared minus y squared. All right, we finally got this x value. But if I plotted this, you know what I mean? What I would get is I throw in a positive value for y. So if I throw it, y is this direction. If I throw in a positive value for y, I get an x value. So if I throw in y is equal to 0, I get the radius. So y is equal to 0, x is a positive radius, that's where it's going to start. And if I throw in a negative value of y, I get a positive x, so it's going to be out there. And as I approach a negative radius, if this is negative the radius, I'm going to square it. The negative goes away, so I still just have r squared. We're going to subtract it from the radius, so this becomes 0. And then hell yeah, that's the distance right there. But I just get that swept out, and if I go in the positive direction, same thing, positive, and it'll sweep out that. So this equation right here is x is equal to the square root of r squared minus y squared. So if I'm taking this and I'm trying to sum from this limit to this limit, like I don't have an equation yet. You know what I mean? So I need to get this equation. So this equation right here is just this equation with a negative sign, and then it'll hit. It's the mirror of that, so it'll just hit all those points. So I have r squared minus y squared. So then when I take my integral of dx, and I'm going to sum all these segments from there to there. My limits of integration are negative square root r squared minus y squared to square root r squared minus y squared. So let's do this one. The integration is going to be x evaluated at the square root of r squared minus y squared, or starting at negative r squared minus y squared to this limit, and then we can throw those in. Sometimes it's useful just to, if you have something in a square root, it's obviously it ain't changing, so you can just say, you can also do this, y is equal to negative square root to square root, and then when you evaluate it, throw these in. I can say, hey, that's just the square root, minus, and then we have minus the square root. So it's the limits of integration are always the the second term minus the first term. And if you swap these limits of integration, then just your integration becomes negative. So I could switch these up like that. Sorry for doing that. It's probably confusing. But you can just know that you can do that. But hell yeah. So this is a minus minus. This is a plus. So we get 2 square root. And then so this integration comes out to be 2 square root r squared minus y squared. And now is that what we see? Is that what we get? And is that and what did we say? It's a horizontal line. So we get this and it's an equation. And, you know, it's a horizontal line, so we shouldn't have y is equal to something. We should have x. And that's what we have. We have x is equal to something something with a y. So that is the equation of this line. And I think it's very, very important to like superimpose these, because you're like, okay, I had this half circle. This is x and this is y. But now what you're saying is that I'm getting x, y. I'm getting an equation that you know, this length is my equation. So if this is my radius, and we're calling this just r, then this length is 2r, and then up here the length is 0, and heck yeah. So then we would get, you know, something that looks like that. So this is x equals to 2 square root r squared minus y squared. And you could even, you know what I mean, you could figure out what this is in terms of y. And so let's do that. So let's get the 2 to the other side. So we have 2x. We're going to square it. That becomes 4x squared. And then that's going to equal r squared minus y squared. So the steps that we did, we took the 2 to the other side. We set that equal to r squared minus y squared. That's all we did. And then we squared both sides. Cool. And then we're going to get the y squared over here. R squared minus 4x squared. And then we're going to take the square root. So y is equal to the square root of r squared minus 4x squared. Cool. So that's the equation of that line in terms of y. But, I mean, this height might be meaningless. I don't know if it has meaning for our problem, but it's this height that we were interested in. So this is also a good skill to be like, well, because let's say that's the first thing you should do is just, hey, rotate this. I think that's the easiest thing, is like, hey, let's bring that x to the top, y over here. Cool. And when we do that, I have this kind of high height, and then I have this shape. And then I think the second thing to do is like, well, we typically don't write equations like this. And so, and then flip this y. So we're going to do that, and we're just going to mirror that image. So that's kind of just a two-step process to take an xy coordinate and make it a yx. Because now we have this, you know, this equation is r squared minus y squared. It's now this is totally synonymous with if you change the variables, and if you chose this as y as this is x, and you did this same shape, you could say this is y is equal to 2 square root r squared minus x squared. You know, just in terms of y. But I think it's useful to do this process and be like, oh, okay, yes, this is the height, and what was this? At y is equal to 0, hey, we get, this is the radius squared square root, so this is just 2 times the radius, and that's what we see. We get that height of 2r. And then when y is equal to the radius, this becomes 0. So this height is 0 right there. All right, hell yeah. And so this is our equation. And this is our equation in a vertical sense. And now you could say like, oh, we could take this dy and then start summing limits of integration from well, and then this, yeah, it's kind of, it's always difficult when you're, you know, this is the same thing. If I'm summing this, if this is my equation for this line, and I want to sum these strips, I'm going to have the integral of this equation for this line, which is 2 square root r squared minus y squared. I'm going to give the height of this equation a little bit of width in the dy, and then I'm going to integrate in terms of y. But this is synonymous with just having a box where this is the x and this is the y coordinate system, and you would have a dx here, and let's say your equation is y is equal to 1, so you're going to have equation 1 times dx, and you're going to have x is equal to, your limits of integration are a vertical line, x is equal to 0, and a vertical line, x is equal to 1. So I think that's easier to see when you're dealing with x and y, when you're like, okay, I'm going to integrate from here to there, I'm having vertical lines, that's the equation of the vertical lines. When these get flipped around, sometimes it's harder to see that, okay, so this, I'm going to integrate from here. I'm going to take these slices and add them from here to here. So this equation right here is y is equal to 0. That's very synonymous with an x equals 0 equation, having this x as our horizontal axis. Our y is our horizontal axis now, so this is a y equals equation. This equation right here is y equals the radius. Sorry about that. Is that even true? Yeah, it's when this radius is r. When y is equal to r, this height becomes 0. So that's the limit there. All right, booyah. So we have. So I'm gonna show it like this, and then we'll go back and just show it in the horizontal. Because it's also good just to be like, hey, I see this. I am making a horizontal line. I know my horizontal is the y direction, so I'm going to have two equations on here. I'm going to have y is equal to negative something something z squared. This equation is going to be y is equal to, positive z squared something, whatevers. And then I'm going to integrate from both of those two equations. That's going to give me the equation of that line. The vertical height, I could, in this regard, that's the same thing as saying, hey, we have a, if this is the equation, this is the y is my height, the z is my horizontal, and when z is 0, the height of this is 2r, and then so I would have that shape. So that is a good process to get into, but it's also just a good idea just to be like, well, just as it's drawn on here, I would have this is the y direction, this is the z direction. At z is equal to 0, my height is 2 radius, and obviously I can just see that, and then there's this, you know what I mean? And I can just tell that this is the, what would you call it? This would be the independent. Damn it! I wish I knew the term. Gotta go look that up. I should look it up right now. All right, hell yeah! So now I can be confident about this. For sure. Let's see what our equation is. We'll even show it horizontally. I don't even know where we're at anymore. But if we have an x, y, and we just have some sort of function. Hell yeah, this is your independent variable. These segments are a number system. There's equal distance between them. They're not dependent on anything. It's set. It's the independent variable. Well, where these heights, it might not change. It might change a lot. Might not change again, and then do whatever. This is your dependent. It's dependent. Whatever value we're choosing along this x-axis determines what that value is. So this value right there is dependent on what we choose, what number along the independent. So cool. All right, hell yeah. So that's going to be useful when looking at a vertical line and then equations of this. So cool. All right, so I think it would be useful to go over this horizontal equation just as it is. And I think let's get a fresh sheet of paper. So booyah. So we have that shape. This is our slice. And we're going to do this horizontally. Cool. You know what I mean? This is a circle. We know that this is the y, z, x direction. This is going to be a little dy slice. If this is the center of this circle, it's going to have a radius. And this radius is going to be a function of this circle. So that's where this problem kind of has to start. We have radius right there and negative r right there. So we should do that. We should, so I'm going to draw kind of a quick separate picture right here. And say if we have r to negative r, this is the x, y. That's the only coordinates we need. I'm going to come out a value in the x. So this is x and y. So it's just kind of good now to like be able to do this on a tilted, playing field. This is the radius. This is the radius. This is the radius. That's the same radius, even though it's kind of drawn funky. So the equation for this, this height right here, this y is height. And that's going to be this, and this is the diameter. So the height of this line, the y of it, it's going to be a function of x, is the diameter. So this radius, what I'm calling r naught, is going to be that diameter divided by 2. This is just the definition of a radius. And if that diameter is this function of y, that radius is going to be y divided by 2. But let's get this equation first, and we can just do that just on the fly now. Because if I know my hypotenuse, this part of the right triangle is going to be the hypotenuse squared minus the other side squared. So that's where this equation should just be very visual. This negative kind of gives it away. Hypotenuse, larger number, smaller number, that's the other side of that triangle. Cool. That means that this r naught is y divided by 2. Therefore, it's this divided by 2. So this radius right here is 1/2 r squared minus x squared. Cool. And we're not going to use, because this is in terms of x, once we differentiate along the x-axis, then we can differentiate that. But if we're just, integrate. If we're integrating along the, if we have something that ever looks like something, r naught dx, then we do have to, write this formally, and it has an x in it, and we have to integrate that. But until that point, this can be just kind of considered a constant, especially when we're just looking at this one slice. Until we start to integrate it, or sum these slices and add those slices. This slice with a little bit of thickness dx, and add up all those slices. Until we do that, this is just kind of a constant. I'm just going to call it r naught. Okay, and then the same thing. We need an equation for this line, so I get to go over it twice. We're going to say this is the z, this is y naught, and then for sure this distance over to here is going to be, so this distance y is r naught plus y naught. But we just know that the equation of this, so that's what I had to do. I had to get this radius, but I knew that this radius was tied into this radius. So that's what I spent my time doing, just to get this equation, which we'll use at the end. So that is important to that. You could have done it the opposite. You can see that now you could have done it the opposite, because this radius, I can kind of treat it as a constant, because it is a function of this circle. And you can see that it's just a function of x. So until I start integrating these slices and adding them along the x-axis, I don't have to bother with that term. And so that's why I'm just going to call it r naught. Okay, so this equation, this z height, again we have this is r naught. We have a right triangle, the hypotenuse. I want to know the height of this, side. And so, just very visually and very quickly, same thing here. You should be able to see is the square root of the hypotenuse squared minus the other side of that right triangle squared. And this is a good intermediate step before introducing what this value of y is, because we have a circle that's shifted. This circle isn't centered along this axis here. It's shifted. And so this equation, I think these are the hardest equations, especially for engineers, because you just get so deep into a specific subject, and then you're just like left with something just a little offset, and you're just like, ah, damn it, how do I get an equation for that? And so we showed it a couple ways, you know what I mean? Just if you're just going to go for it, hey, this distance is y minus r naught. Or you can say r naught plus y naught is equal to y, and then just solve this for y naught. And so that's what we're going to do. Y minus r naught is equal to y naught. And you should spend half your time solving for the variable and having it just live on the right side. I'm trying to do that more, you know what I mean? Because, it saves on paper, and it saves the fact that you don't have to do the mental manipulation and do two steps at once of being like, okay, I'm going to get this to the other side, but then I want to flip it. You know what I mean? I can just be satisfied with, hell yeah, I solved for it. So now this z is square root r naught squared minus y minus r naught squared. Cool. But again, we're going to be summing these horizontal components. So my limits of integration, this is that dy slice. So back to here, we got dy, and I need my limits of integration to be in terms of y. Well, y is right there, so we need to solve this whole thing in terms of z. And we just know that we're going to get this chunk of a circle, and so we need the opposite, which is just going to be the negative value of that. But in this case, it's going to be a little bit funky. It's when we take the square root. It's not just going to be the function minus. So I'm going to show you that, and that's where I could make mistakes. And that's where I need to double down and watch more videos on square root. You know what I mean? Just anytime you see a square root, just always know it's just like, well, there's going to be a positive and negative here. But if it's already specified, we're just interested in the positive root. But now you'll see that when we solve for y, we're going to get a positive and negative root, and we're going to show those. All right, so we're going to get z squared is equal to r naught squared minus y minus r naught squared. Should we do this in 1,000 steps? We're trying to solve for y. So, let's get this whole chunk over here. And you might as well, if we read left to right, I'm always looking for that, getting what I'm solving for on the left side. It is helpful for me. So y minus r naught squared, get that over here. R naught squared minus z squared. And this should ring a bell. This is the hypotenuse minus one of those side squares. Hell yeah. And we're trying to solve for that side. But you can see that it's not just the side of a right triangle. It's this extra length right here. Okay, so now we do the square root both sides. So that's going to be y minus r naught. Once we take the square root of this side, is equal to, so now I'm going to do plus or minus the square root of r naught squared minus z squared. Cool, so that's where the plus or minus comes in. And we're, for the time being, let's just worry about the plus and know that we can switch it to the minus also. Because if you're not, paying attention, you're not going to do the negative root. And then so, okay, we still need to solve for y, so we need to add r naught to the other side. So we're going to have r naught plus the square root of r naught squared minus z squared. So here's our equation for, well, we need to see what this equation is. If I throw in a z value, I'm going to have this radius squared is the hypotenuse. It's always going to be bigger. So if I throw in a positive z value, I'm just going to get a positive, let's see, what is this going to give us? Oh, and I got to be, oof. Yeah, let's do, yeah, this is the y, z plane. Let's just throw z is equal to 0. So z is equal to 0. What's that going to give us? That's going to give us, r naught squared plus r naught. So this is going to be the radius plus the radius. I'm going to be out at that point. But you can see that this should also give us this point. You know what I mean? And if we throw in that plus or minus, it does. So if we throw in z is equal to 0, we're going to have the radius, r naught minus the radius. And that's going to be 0. Cool. So, and then we got to split our equation in half. So this part of the equation is y is equal to r naught plus the square root of r naught squared minus z squared. This part of the equation is y is equal to r naught minus the square root of r naught squared minus z squared. You know what I mean? But it's not just this equation. It's not just this side isn't just this equation, but the negative of it. The negative is because of that root. You have a positive and a negative root. That's where that comes from. So at least I can recklessly say that, but still, I need to get better at. I mean, just the fact that yeah, if you pop out a square root, if a square root comes into being, you know, it's got a positive and negative root. Just pay attention to that. Especially for these calculus problems, because yeah, that side is needed for this. So now we're going to have our limits of integration of this dy. And we're going to start from the negative root. So we have y is equal to r naught minus r naught squared minus z squared. To y is equal to r naught plus r naught squared minus z squared. Cool. And this is where it is useful, because you might make mistakes. It can be useful just to be like, hey, this is the integral dy of r naught plus a square root, r naught minus a square root. The stuff in the square root ain't going to change. You're going to do this integral, and you're going to get y evaluated at r naught plus square root, r naught minus square root. So when we throw this in, yeah, probably just have just enough space. When we evaluate these limits, it's the second minus the first. We have r naught plus the square root minus r naught minus the square root. Whoops, I didn't mean to put anything in there. And this is going to be r naught plus the square root minus r naught. This minus and this minus make a positive. And so you can see that the radiuses drop out, and we get 2 of the square roots. And again, what is this? This is an equation. You're taking this length of this line, but we're gonna vary them. So it is in terms of r naught, and r naught was in terms of x. So you know this line. Well, yeah, I guess this line is in terms of r naught. I said that we're gonna worry about later. We're treating that as a constant, but it's in terms of y now. Damn it, it's in terms of z. Yeah, so this was this equation, y is equal to z, you know, where z is the independent variable, and the height in the y direction is the dependent. And that's why it is useful to do these calculus problems horizontally, where this axis becomes your independent. You know, like, hey, your y is your dependent, and your height is your independent. And so, yep, so inside this square root, I guess let's write it out, is r naught squared minus z squared. And so this gives us an equation y. And so, you know, and then it's very useful because the height of this line doesn't start anywhere, like the height of that line. When we vary the z, see that's what we have this equation, and when we vary the z value, when z is 0, the length of this line is 2 times that r naught, 2 times that radius. And when we take a z value up to this radius, r naught, the length of that line is 0, because this minus that is 0. So z is the independent variable. But see how, like, if I get the length right there, it doesn't start, it always starts at like a new little axes, you know what I mean? Like, hey, this starts there. And so the cool thing about integration is it takes this line and makes it an equation where you can still draw it, you know, like this axis where we have z and y. And it says that, and this is r naught, and this is 1, 2. This is 2 r naught, and this is r naught. It says that when z is 0, we're here, and so you get, but you get length right away. So like if you're up here, you're getting length right away. So like right here, hell yeah, you get some length. Here, like where does the length, like this length is about the same. So even when you're right here, hey, the length's about the same. And so you get this shape. It's always good to like kind of draw in the shape that you might get. And this equation, you know, you can say, hey, this is the independent variable, even though it's sideways. You know what I mean? It's this height that we're interested in. So it's good to be able to do a problem sideways. Like it's also good to like, and if you're not able to do that, to turn this. So the two steps to turn this are, you know, go y, z, and then I just flipped it up. So now it looks like that, but you should probably flip it the other way, y, z, so get the positive z-axis this way, so then it flips that way. And now you would have this. And because this is my y, you know, y and z, you know, I mean, this would be y is equal to something something z. And that's kind of what we're familiar with, where this y is the height. So just laid down on the side, this is still the height, but in terms of this dependent variable. So the same equation, y is equal to, and what's this equation? 2 r squared minus z squared. Same equation, y is equal to 2 r squared minus z squared. But yeah, those are the things I like. I'm glad my camera cut off yesterday. Like I was just recording 3 hours without sound, and that kind of bothers me. But not really, because like I'm still, I don't know, you know what I mean? I'm just doing this to get better at teaching. And I don't see anyone else putting themselves out there in long format ways like this. So I think it is useful. But it is difficult, because the second you have a question and you want to figure out something, you know, that might be an hour long, you know, and you might kind of mess up. You might do something, because like you still have to follow like laws. That's the cool thing about math, is like it's following, well, especially calculus, is following continuity and following, you know, logic and continuity, mainly continuity. And so you can pretty much prove anything. It just takes a little while. But if you make any mistakes, if you drop a consonant or change something, a negative sign, man, that can really destroy the meaning of something and can mess you up. But hell yeah, we're doing pretty good. All right, hell yeah. So, and then we kind of have the light at the end of the tunnel. Okay, so we have this horizontal line as y is equal to 2 r naught squared minus z squared. Cool. Now, and we have that. You know, you could treat it like this. I mean, you don't have to treat it like this shape anymore. You know what I mean? This shape is the same as that shape. It's kind of bizarre. You know what I mean? The area of this shape is the same as the area of that shape. But let's grab a fresh sheet of paper, because now we're needing to, like all we have right here in both of these pictures is the equation of a line. It doesn't have any more dimension than that. It's one-dimensional. But that's I'm still proud of this video and going through it, because a lot of calculus already starts with some sort of equation and you already get a slice. And it's just like, no, you don't. I mean, I think it's useful to be like, hey, if you're going to go that route, do this, do your little dy, and then integrate it. Sure, and if it's just a normal xy equation, you know what I mean? Hey, this line right here is y is equal to 0, and then, hey, this function is y is equal to something. So your limits of integration are 0 to literally that equation, you know what I mean? So the equation minus 0 is the equation. So that first integral is the height, but I just think it's very important, especially start with that first element in the direction that you want to take your height equation, because you might want to take your differential element that way, dx. And yep. And even you know, it's also good to every once in a while say, hey, this is like this differential element is literally a point, or not even a point, or it's nothing. It doesn't have any dimension in any direction until like you start to give it a little dimension in a direction. That's why you can either start giving it dimension that way, you can or start giving it dimension that way. But yeah, that's where I thought it was useful to do this route instead of saying, oh, I'm already trying to find the area. Let's just call this a dA chunk, and where dA is a dx dy. But if you do that, sure, you can integrate still. You're still going to integrate the same, but after you integrate and you get this thing, this still has 0 area. You know what I mean? It's still a line. And that gets, you know what I mean? It has 0 area. It does have height. It has sufficient height. The height is the equation of that. It's the same thing. It'd be synonymous with like, hey, I have this little chunk, and it's you know what I mean? I have that, and inside this little chunk, I'm gonna take a volume that has a dx, a dy, and then into the board dz. And then I'm going to integrate it maybe horizontally first. We've been doing that. And then I'm going to integrate it vertically till these points. And then that gives me the disk. You know what I mean? So then I get some sort of disk in here. But still, even if I did that, if I did those two integrals, I have a disk with an area. And even if I gave it a little dz width, it still has 0 volume. You know what I mean? This dz is approaching 0, where it's only until I actually use the rules of calculus and start adding up those slices am I giving it volume. And so that's where I think it's like, if we drew this same shape, I think it's important to be like, hey, you know, and even, because I even started with a line, you know what I mean? Where you could start with a point and be like, what direction do you want to start? Like, the first integral is going to be a line. Like, where do you want to go? Do you want to go, like we've been going horizontally, and then we're going to add those up to there, to there. And then once we get that equation for a line, then we can give it, we got 2 different directions to give it width. I can give it width this way, or give it width that way. But still, this is a line. It's still one-dimensional. It for sure has length now, but it has 0 area. Just as when I give it a little bit of, so, you know, we did the dx, you know, maybe the next thing to do is give it a little dy, and booyah. And then I can kind of sum, you know, these little slices all the way to here, you know, down this shape. When I do that, hell yeah, I get an area, for sure, with actual area. That is now area. But the second I give it a little dz slice, it still doesn't have no volume. Volume is still 0 until I start integrating. And so, yeah, I just think that's, I think that's useful. Because when you do this, it seems like if you start with this differential element that already has the 3 dimensions, what happens is this, is you start with that differential element that looks like that. So when you do integrate from here to here, it looks like you have something more than the line. You know what I mean? It looks like you have a bar of something. This bar does have length. For sure it has length. But this bar literally has no depth, and it has no width, you know what I mean, per se. Until you integrate, you know, along, you know what I mean, you know, the other directions. Once you do this, then you So if you started with that differential element, you get this bar that has length. It's just the equation of a line. Like, that's the hard thing to see, that, what, that's just a line? Yes, even though you're actually representing it as a bar, like, this is dimension. The only dimension it has is length. The other dimensions are 0. It has 0 volume, it has 0 area. And then the next thing we do is we take it up to here. And then, and if you took this bar and then took it up here, then you already kind of specified that it has this dz, because you started with that differential element. That's all I'm getting at, is like, I don't like the fact that you start with this differential element and no one's teaching it as like, hey, start with a point, you get a line for sure, 0 area, then differentiate, add those up, you get an area, 0 volume, instead of starting with this differential element, because the second you take it up here, it now looks like you don't have a disk, or it looks like you have a disk, but then it looks like it has some sort of volume. And it technically does and doesn't, Like, this dz is supposed to be approaching 0, meaning like it doesn't have volume, but it has more volume than 0 volume. So that's the trademark of this little dz. That's why I like to think of it in practical terms of just 1,000th of something. If these are as long as your lengths and widths and heights are just normal numbers, like, sometimes you can't go wrong with having these dz's be 1,000th and then just adding them all up. You'll get a little bit of error, but typically nothing doing. Alright, hell yeah. So now we're ready to take this home. We got 2 more parts to go. Actually, this next part is the harder part, because we have to find the area of this. And if this is our line, it's in terms of z, we need to give it a little bit of width, dz, and then integrate it. So we're going to integrate this equation, dz, from z is equal to 0. And then here we just have to go z is equal to r naught. That's all we have to do. There's no bounded equation. But when we integrate this, look, it's in terms of z squared. So we can't use u substitution. If you use u substitution, you'd have to have a z out there. So that's where we have to use the trigonometric identity. For most purposes, you just say that, oh, this is just the area of a circle divided by 2. It's the area of a half circle. So, like, why even do the trig identity? And we're going to show that even the trig identity, it's like, it's a lot of work for a reward. It's less. It seems less exciting than it is. So that's what we're going to go over right now. Okay, hell yeah. So let's redraw this. And this is kind of one of the strategies that I use, is like kind of turning math and physics into juggling, where you're like, hey, can we crank out? But now we just got to get on with it. I don't want to crank that out again. But we do have the equation for this line. That's what we have. So we have z. This is the y, this is the x-axis. So we have z is equal to, and it was 2 r naught z. So we have 2 r naught squared minus z squared. So that's the equation that we have for that line. And we're going to give it a little bit of dz height at a distance z away. And we're going to integrate from z is equal to 0, that line, to this top line at the top of this semicircle, z is equal to r naught. So that integral looks like this. We have r is equal to 0, z. So we have this equation, dz, the limits from 0 to z is equal to r naught. Okay, hell yeah. And we can't, like we said, we can't use u substitution. If you go to like Google and be like, what's the easiest like integrals? I mean, I don't know, like you can say it like this. If I can't use the power rule, what's the next easiest way to do? I don't know. It's like, but there's there's u substitution. If you can't use u substitution, you go to trigonomic identity. If you can't use trigonomic identity, I think there's some other tactics. Well, no, you do. If you can't use u substitution, probably the next one is what was the integration by parts. If you can't do integration by parts, then you're looking for trigonomic identities. If you can't solve this integral based on trigonomic identities, then you're looking for, it'll say numerical methods. Definitely Excel. Because all we're doing is just trying to find the area of that shape, and for sure the area of that shape and all these shapes, and we're going to add them up. So Excel would be perfect for that. So that's what you could do. All right, so, but booyah. But trigonomic identity, this is kind of a cool one, and I think I'm pretty good at explaining it. I've only done it this week, so it's pretty sweet. But it's just the area of a circle, or area of a half circle. How do you could do it the area of a quarter circle. But just, if you're trying to integrate the equation of that line to get the area of a part of a circle, like what do? Well, you use, so we're going to come in here, and we're going to, draw our little, this is R naught. What is this? This is Y naught. And what's this? This is Z. So I'm gonna draw that again. Because it's just fascinating how, like, hey, we're actually going back to that. So we have our Y naught. That's in the Y direction. This is the Z direction. This is Z. And then we have R naught. Cool. So what we do is we throw a little angle in there. And this is where we use, we try to change our variables to things in terms of theta. So we're trying to get rid of like the xy. In this case, it's the yz, y naught z. And so, so just right here, we have a, we have a right triangle. We know Pythagorean's theorem. We also know that with an angle, this height is proportional to the hypotenuse. We talked about that. Like, just visually, it looks about like 80%. And we talked about how, like, sine of an angle is a percentage. So I guess we didn't specifically talk about that. But here is your cosine component, because it's horizontal. This angle, if you draw some sunshine and rays, shines at the sining side, the sine component side. And so, and the sine of an angle, like if you put this angle into your calculator, it'll pop out probably about 80%. And that's this height is 80% of the hypotenuse. If you typed in cosine of whatever angle this is, you would get this percentage, which looks like 6. Yeah, this looks like that 3, 4, 5 triangle. So this looks about 60%. That's what you would get. Yeah, and that's important, because you shouldn't. I think you don't have to go too deep, but that's the first perspective on sines and cosines. If you see a sine or a cosine on your paper, and you're just like, I don't know what that represents visually, or more than just an equation of like SOHCAHTOA, which I think is an awful acronym. Oh, my camera's gonna overheat. All right, hell yeah. So took a little break, cooled down the camera, and hell yeah. So we can represent, I was talking about, trigonometry, man. It's good to know sines and cosines as percentages. And so, and if this hypotenuse has a radius of r, if it has a radius of 100, 80%, is 0.8 times 100. That's that length. So that's a better mental way. And in engineering, you do this all the time. You have a vector, some sort of force in that direction, and you want to know the component of that force in this direction and that. It's always going to be less, you know what I mean? And so yeah, and it's going to be that percentage. So you're going to take that radius, r naught, times that percentage, cosine theta. And so you can just kind of see this visually, that that's going to be this cosine or adjacent component. If this is the angle, this is the opposite component. So so our equations for this are going to be z is equal to the hypotenuse sine angle. This length, y naught, is going to be the hypotenuse times the cosine of the angle. So you can see, take the bigger number, take a percentage of it, hell yeah, that's the side of that triangle. Alright, so for our substitution, hey, look at that, there's z, booyah. And then this is dz. So I think this, gets overlooked too. So we're going to take dz we're going to take the derivative of this function, but with respect to what? We're going to take it with respect to theta. So we're going to go dz d theta. And, you should always occasionally write this out. This is d of this function. So this is r naught, sine theta, when we change theta. You know what I mean? And if you can graphically do this, it's like, hell yeah. I don't know if I could on the spot, but, I mean, hell yeah, we should. I mean, because, what we're going to get is, like, what do we... Like, if you're taking the derivative of something, what are the rules of derivation? One is that if you have a constant, as constant, you can just take it outside. So this is going to be r naught derivative of sine theta d theta. Now so we have this function now is just sine theta, so it might be easier. This is important. You should also have this on lock or figure out how to draw this to scale. This is how I do it. I'm just worried about the first 90 degrees, which is 30, 60, 90. And then I try to do these, in proportion. So this is, and then this could be like 1.57 radians, basically 0.5, 1 radian, and 1.5 radians, if you want to think of it that way. This is going to be pi divided by 2. And then you got to divvy that out. So, ugh. Like, I'm not very good at the fractions, but obviously it's going to be a third of a half. That's going to be pi 6. This is going to be 2 thirds of pi halves. Ugh. 2 pi 6. And then, yeah, that's so. You should just leave it as 2 pi 6. But you would say it's pi thirds. Ugh. Fractions, it's just like, they're not visually very good. It's like, it's very, very difficult to see, the difference. But anyway, so we have 90 degrees, 60 degrees, 30 degrees. Sine is going to go from 0 to 1. And so how I draw sine is like, hey, you're going to have a slope of 1. Sine of 30 degrees is a half. And then I just keep going. It's linear, like the small angle, is appropriate up to 60 degrees. I use it all the time for guesstimating. So this is your sine graph. Hell yeah. And if you did the next 90 degrees, you would take it flat and then come back down. And, if you did that twice, you go up, over, down, over, up. You know what I mean? And then you get your sine graph. But if you trace this out, hell yeah. Like, that's the actual... that's the actual graph. And then, so see how I can't do it very good by hand? But that gets you really good. And so, and especially drawing this slope of 1 with radians is very important. Because the derivative says, hey, I'm going to change this, and then I want to know what the value is. So I'm just going to change my radians from 0 to 0.5. So that's going to be this 0.5, so 0.5. And then how much did my sine change? Well, we're going to go from 0 to 0.5. Oh, okay, look at that. Hey, we changed by 1, slope of 1. That's basically what that says. Now let's come up to, here. And, hey, the slope is 0. Approaches 0. But at least that gives us a start that says, hey, this is a slope of 1. The quick way, so that was, at least we did one of them. You know what I mean? Where we threw in a value. Well, we could do it. We could say that the next change is still going to be 0.5. If we go from here to there, still we got about a 0.5 radians. And then what does sine value? What's the sine of 60? Sine of 60 is 0.866. You know what I mean? That's that square root 3 divided by 2. And we started at 0.5. So what's 0.866 minus 0.5? We get 0.366. So we get less. See what I mean? So then we're getting less than 1. And so there you go. So our slope is less than 1. I'm sure, like, you know, oh, and then you could just double this. You know, 0.5, you could double this. That would be 1. And then double this. Oh, well, what is doubling this? That's 0.6, 1, 2, 1, 2. And we get 2, 3, 7. Oh, yeah, check it out. That's square root 3. Okay, sweet. So, feel like I did something wrong there, but no, maybe not. Shouldn't it be square root 3 divided by 2? Oh, yeah. No, this has no bearing. Sure, this is square root 3, but you know, we did such huge chunks. I mean, to actually hone in and get, like, what we just said was we did a secant, you know what I mean? So it's always good to, like, you know, kind of, I don't like the technicalities of differential calculus or calculus in general, but it's just fun to see, like, when you do something like that and you're just stumped. Well, it's just because we took a huge change in theta. You know what I mean? You need to take a small chunk. You need to, if you're going to hone in on that midpoint, you need to change this angle just by a fraction, which you could in your calculator, you know, and then get some sort of value right there. Same thing for right there. Any of these, you know, they're going to approach a number. So, but anyway, we're just it's good to throw in a couple values. Definitely, all we're doing is taking the derivative of sine theta. So we have r naught derivative sine theta d theta. I always like to draw and then here's how I'd quickly draw the sine graph. You know, like this and that. Cool. And then the cosine graph is like that, and then this. The cosine graph, so the things to note about the sine graph: the slope is 1. Slope of 1 right off the bat. Cosine graph, slope is 0. But the other thing to notice about the cosine graph is that besides just the point right there, every other point is going to have a negative slope. So those are the two things that you need to pay attention with the derivative of a cosine graph is negative sine. Because when we throw in a value of theta equals 0, on a cosine we get, if our equation is cosine theta, and we're trying to find the change in this value when we change theta, look, it stays at the same location. You know, that's the other thing of the cosine graph. It's always up there and then starts to come down. So there is no change. With an angle of 90, there is no change. And so that's I'm horribly sorry. Obviously, cosine is 1 when the angle is 0. So if this is the cosine graph, when the angle is 0, your value is 1. When your angle is just a little bit like 0.1, hey, your answer is still 1. That didn't change at all. So what equation, when you throw in theta is equal to 0, do you get a value of 0? Well, that's the sine graph. So holy hell. So if here is the sine graph and here is the cosine graph, the derivative of the sine graph is cosine, because right at theta is equal to 0, I get a slope of 1. So what equation, when I throw in theta equals 0, gives me 1? Well, cosine 0 is 1. So the derivative of sine is cosine. But the only thing with this, like I said, you have 0 slope right off the bat, but you have a negative slope overall. So cosine theta, when you throw in a value, so if you have the derivative of cosine theta, the slope is 0 at 0 degrees. So what equation, when you throw in 0, gives you 0? Well, sine theta, when you throw in 0, gives you 0. So that's the derivative of cosine, but it's a negative slope. So that's the way to remember that negative slope. That's how I do it. So again, derivatives, I do sine, cosine. This is slope of 1. Sine goes to cosine. Cosine, slope of 0 at the start, that goes to sine, but overall it's a negative slope, so it's negative sine. So those are the derivatives. And then, and we're going to do the antiderivatives, but you still want to just use your knowledge about derivatives. I mean, because integrals, how do you integrate these? Well, you start with the equation and then differentiate it. And then you should be able to get back to the equation that you're trying to integrate. So, and then we'll talk about that later. We need to move on to hell yeah. So what we did is we just differentiated this hardly. And so we have d sine theta, d theta. What's the derivative of sine? I'm just going to quickly do a sine graph. It's positive. Slope is 1 right at the beginning. So we have cosine. So this becomes r naught cosine theta. And the derivative is, so this is the other thing. You know what I mean? You might not do this, but we have to use, well, it's, you're using, damn it, I forget what problem, but you do have a d theta here when you differentiate your, the derivative of this equation with respect to theta. Nah, damn it, no it's not. Okay, sorry about that. Yeah, sorry about that. I was thinking the chain rule. You know what I mean? That's what I was thinking. We can do that. That's a good trip to do. So if we have dz d theta, this is our equation. So we have d r naught sine theta d theta. Hey, we have a product of two things. Let's use the chain rule. Chain rule says it's the first times the derivative of the second plus the second times the derivative of the first. Well, this is a constant, and so when we change theta, this value always stays the same. So when we use chain rule, this side goes to 0, and we're still just left. That's the definition of being able to, if we have the derivative of this, how to get that constant outside of the differential equation. So how can you bring that outside of that differential equation? So that's how you do that. All right, and then we have r naught sine theta d theta. But I guess pay attention to this, because this is still the derivative of this equation with respect to theta. So we still have dz d theta is going to be r naught cosine theta. So this is the equation we get, and it has 3 different parts to it. And so when we do our substitution, I have one of those parts right there. So check it out. I have that dz. So, you know what I mean? And this comes up a lot. Is like there's a lot of equations, especially in electrical engineering. What is it? IRV? I don't know how the letters, you know, I don't know if it's I divided by R, but hell, you can rearrange this 3 different ways. I shouldn't have done that because I don't know how that equation goes. I'd have to look that up every time. But anyway, so yeah, you can rearrange this equation 3 different ways. So we could say dz is equal to r naught cosine theta d theta. But this comes up a lot, and it's a good tactic to do. Yep, and you could also say d theta is equal to dz divided by r naught cosine theta. I mean, you do whatever you need to do, but those are the 3 different ways to represent that. Cool. So we're trying to use trigonomic identities to get rid of these variables, this z and this dz. So it looks like we came up with a nice equation for dz. And then for z, we got this equation right there. Hell yeah. All right, so, oh, and this is fascinating because we don't need to deal with this why not term. Had we integrated in this linear direction vertically, we would have contended. So that's where I am going to do this one more time, this whole trigonomic identity with a vertical line, because then you actually have to sub in this term. I just got these terms at the ready because I thought I was going to have to use them. But yes, if you get this vertical line, you know what I mean, you have to sub in these terms. Like everything cancels out, it just seems a little bit messier. And so it is kind of good to notice that. All right, hell yeah. So let's substitute. And then the other thing that we got to do is like, hey, if z is 0, So now we have to like go back to this equation. So if our limits of integration say z is 0, well, we're changing all this stuff to theta, like d theta, theta. So this limit of integration, if dz becomes d theta, our limits have to be in terms of theta. So if we throw in 0 for z, this equation, we get 0 is equal to r naught sine theta. Now, this is a good math tip. Is like you should never just divide. You should never take this and take 0 divided by that. Anytime that you get an equation with 0 and you have a product, you should represent it like this. R naught product with r naught sine theta. And realize that if either one of these terms are 0 unto themselves, it makes this equation satisfied. So you get two equations from here. So you get 0 is equal to r naught, and you get 0 is equal to sine theta. Both of these equations will satisfy. We're interested in what theta is, so this is irrelevant to us. So now we have 0 is equal to sine theta. Let's write it sine theta is equal to 0. And then we're going to take the inverse sine of both sides. I never like to write it like that. I just like to know, hey, just go theta is equal to the inverse sine of 0. But, sorry. So theta is equal to the inverse sine of 0. But now here is a pro tip. Because the sine of the angle is a percentage. Like, I like to think of it like that, but then I probably lose my mind a little bit because it is SOHCAHTOA. It is a, it's only a percentage if you multiply it by 100%. Else it's a fraction. It's saying, hey, the length of that side is, yay, this number, compared to the hypotenuse. So even if I have this, sine of the angle is equal to 0, like right here, this is a proportion. So make it a proportion. So this says that I have a triangle with an angle where my hypotenuse is 1 and my sine component, this component right here, the opposite component, is 0. So let's start making this triangle to where this actually becomes 0, and you can see, oh, this triangle is actually just a flat line with 0 height right there. And so that's that triangle. And you can say, hey, if the angle of this triangle is this ratio. So there I didn't even have to go to inverse sine. But if we go to inverse sine, same thing. If I say, hey, this angle, if I do the inverse sine of this, if I'm trying to find an angle, this is going to give me an angle. But to get the angle, I must be taking a ratio. So that's what this is. So turn it into a ratio. Never make the mistake of turning an angle like 30 degrees into a ratio. But hell yeah, literally, yeah, it's like this pops up and you don't know what to do with it. You just have a number hanging out there. Well, hell yeah, turn it into a ratio, and that's a triangle. Bottom is the hypotenuse of 1. The sine indicates that we have an angle here. This is the sine component, the opposite. And guess what? It has a dimension of 0. And then, and then start making it look like that. You're like, okay. And then, hell yeah, that's your triangle. And guess what the angle is, starting from this axis? Angle 0. Cool. So there you go. So inverse sine of 0 is 0. Booyah. So then that's our limit of integration on here. So we have theta is equal to 0. If we have theta is equal to r naught, let's do that one. I'm sorry, z is equal to r naught. So here's our equation for z. We're going to throw in a r naught into this, and we have r naught sine theta. All right, now this isn't 0, so we can divide the other side. So we got r naught divided by r naught is equal to sine theta. This is a ratio of 1, so we have 1 is equal to sine theta. It's at this point that we could just say, whoa, okay, this is our angle, this is our ratio, and so you could turn it into a ratio right now. I kind of wait till that second step, so I'm going to say theta is equal to inverse sine of 1, and now I'm going to turn this into a ratio. Dealing with the sine, so I have just an angle, draw a hypotenuse, and now what this says is that the sine component, this is 1. Okay, now let's start making it look like 1. If this is 1, this is 1. Well, you know what I mean? So you're going to get a vertical line. So booyah. And if this is, if we're taking angles from here, that's going to be an angle of 90, or pi divided by 2. If this whole thing is 2 pi radians, this is pi, was 180. Pi divided by 2 is 90. All right, so there's my limit of integration on that. We have theta is equal to pi divided by 2. Okay, so, and now we're going to throw in these values. So we have 2 square root r naught squared minus, and we're going to throw in this value for z. And so I'm going to have it squared. So I can go z squared is equal to r naught squared sine squared theta. Cool, I can put that in there. So we have minus r naught squared sine squared theta. Cool. And then we have this dz component. So we have this right here, r naught cosine theta d theta. And now let's write this on a new sheet of paper. All right, hell yeah. So we wrote it on a new sheet of paper. I'm kicking myself for not putting the 2 outside, but let's just do that so we can get that constant outside of the integration. So now we're going to integrate this. So the same principles apply as just like, well, can we? You know what I mean? Like, I don't know. So there is a realm of simplification. We see some sine squareds. So, you know what I mean? The first thing, like with this, you know, if you're integrating a true portion of a circle, like this, this trigonomic identity will always play out. You know, even because I'm going to show you when we do the vertical line, it seems like it gets a little messier, but it plays itself out. So what we have here is we can factor out this r naught squared, and we get 1 minus sine squared theta. Now this is where you have to do your due diligence of being like, yeah, just the common. Like, I don't like the unit circle, but that's probably why I don't see these relationships in terms of the unit circle. If this is my hypotenuse of 1, I could say this is x and y. And hell yeah, this is cosine theta, and this is sine theta. You know, so, and this is the hypotenuse or the radius. And so I can see that, hey, sine theta squared plus cosine theta squared equals the radius squared, 1 squared. So I can see that. I can say that what we've been doing is like, hey, what's the equation of this height right here? Well, that's going to be sine theta is equal to the square root of the hypotenuse squared minus this, you know, cosine squared. Cool. And the opposite is true. If I want to find this length as a horizontal length, because we've been doing that with calculus, is like, hey, sometimes you got to treat this as your independent variable, and this is your height of this equation. And so this is going to be, we're trying to solve for cosine theta. And we have cosine theta is the square root of 1 minus sine squared theta. But obviously you also kind of want to write these, you know, not square them and say sine squared theta is equal to 1 minus cosine squared theta, and cosine squared theta is equal to 1 minus sine squared theta. So then when you see something like this, you're just like, oh yeah, you know what I mean? This is, you know, you put it, yeah, so if this had a square root over it, you know, that should be screaming, hey, hypotenuse, bigger number minus the other side, and we already talked about how that's a percentage. You know, it's that percentage squared. It's that side squared. This is the hypotenuse squared. 1 squared is just 1. That's why it's kind of hard to see these identities, because no one's going to spell it out for you and put a squared on that 1. No one's going to write it like that, which might be more helpful. But that's where I don't like the unit triangle either, just because it's just like, what does that 1 represent? And it's really difficult to see that 1 represents a bigger number. You know what I mean? The hypotenuse is always the bigger number. And that, I've never said that before. I'm going to say that some more. But for sure, it's very difficult to see that that 1 is the bigger number. Because sine theta is always a percentage, usually between 0 and 1. So if it is a percentage that's like 0.5, you square 0.5, you get 0.25. You're always getting a smaller number. So, cool. All right, hell yeah. So yeah. So what do we have? So we have the square root of all this. We just factored out the r squared. We got 1 minus sine squared r squared And then here's the other trick. Anytime you have a product of two things underneath a square root, like this happens a lot, but then you just don't know how to apply it, what you just get in the habit of like, hey, just squaring these things individually. So I have that, and then the square root of 1 minus sine squared theta. So like even like right here, this term is just r naught. So booyah, it just popped out. So now this term is out of the square root sign. This we said is going to be cosine squared theta. So we have cosine squared theta, square root of that. Oh, same thing. We have r naught cosine theta. Okay, so this whole term just became r naught cosine theta. Don't forget about this thing, because hey, we got an r naught and an r naught. We're going to square those. And again, these are in terms of x, back to the original problem. I said, hey, that r naught is in terms of x. Don't have it on that sheet. But don't worry about it until we start integrating along the x-axis. It's just a constant until you do that. And I think that's going to help me learn multivariable calculus. I just picked up a book, and it's funny. Like, I love the humor, especially, nephew took multivariable calculus, and, I was just like, oh, yeah. Like, all I could think is just, like, integrating triple integrals. That's what I thought multivariable calculus is. Like, no, the variables are on that side. It's x, y. You know what I mean? But yeah. So I'm looking forward to that. I don't know if I actually took multivariable calculus in engineering. Like, I'm sure they taught it, but I don't know. You know what I mean? That is fascinating to me. I have no idea. But hell yeah. So, and that just like, so all these textbooks are online. You know what I mean? But it's a pain in the butt to like take a PDF and try to get to the juice. Where, like, I truly recommend buying old editions of textbooks, like the one that's going to come. I haven't ordered it yet, but it's like $7. You know what I mean? So you shouldn't be, after shipping, you shouldn't be out more than $15 for like a textbook that at a college campus, the newest edition is going to cost you $300. It's outrageous. Okay, hell yeah. And I do not like the calculus textbooks, because it's a mountain. It seems like a mountain of technical, like it almost garbage, you know what I mean? But it's just like, I don't know. I mean, I guess that's just the way calculus is. I would rather learn that later and then just have aha moments, but I'm not the type to like, look at, anyway. But yeah, it's fascinating. And that's true, because some of that stuff is just like, it's too much. Where my favorite class was numerical methods, and we went back and just did stuff that I can just do on Excel now. But I mean, when someone says it's a 400 level class, and I don't know, like the teacher just made it easy, but in a good way. We learned a hell of a lot. Sometimes that's very useful when things like where you can just plow ahead. And that's what I try to do in my videos, is just like, you know what I mean? You shouldn't feel like you got stuck a mile back there and you're still stuck on that, and everything else is just like, no, I can't handle anymore. So yeah, that was pretty sweet. Okay, so what I want to do with this r squared, we're going to square them, is just bring them outside the integration. So we're going to have 2 r naught squared outside. We have 0 to pi over 2. These are my thetas. And so what else do we have? And so now we just have cosine squared. But this is, so that was just substituting trigonomic identities. Like, that was probably the easier portion. Like, you could probably do that with any problem. And I should do that with other problems, to be like, oh, does it make sense to throw in trigonometry? Just the fact that x equals cosine theta. That's kind of fascinating. Anyway, all right, so we get cosine squared here, and we just can't integrate it. We get it's almost a nuisance. It's the same nuisance of having the hypotenuse squared minus x squared, where this is y, and we're trying to integrate y dx. Using u substitution, we don't have another x out here. So if we have this dx right here, and we're going to try to integrate that, we just don't We just can't, you know, so then we have to use, all right, so I'm going to write this, and then, hell yeah, this is the secret sauce of integrating a circle, half circle. And I think I do a pretty good job because, like, I try to look for the geometry. Like, if you can see it, I think you can believe it. Okay, so yeah, what we have here, I mean, and then you could be like, well, isn't cosine squared just 1 minus sine squared theta? Yeah. And then can't we just divvy up that integral twice? But yeah, you're still left with sine squared theta d theta, and you just can't integrate it. Same problem. So, you know what I mean? So I don't know how you're going to make the association, like where, like, hey, where have I seen this pop up? You know what I mean? You're trying to look for things that you've done in trigonometry where you had at some point a cosine squared theta, or like a cosine theta, and then you know, plus maybe something else, minus something, who knows? But then maybe that was equal to cosine where you just had theta. You know what I mean? Or just a sine theta, you know, where you just, you know, sine 2 thetas. That's kind of what we're getting at. But you see how, like, hey, if this we can integrate, you know, use substitution, cosine u, u is 2 theta, du is, you know what I mean? If we have u is equal to 2 theta, du d theta is, you know, and how we'd write this, it would be 2 theta d theta. That is the same thing as derivative of u d theta. You know, this is the function that we're putting in. And then we get, oh, and this is a fascinating way to do it, because we have a constant here. We can break out the constant of integration, and we got d theta divided by d theta. This is 1, and so we just get 2. So that's differentiating du d theta. But don't forget that we have a du and a d theta is equal to 2. You can rearrange this in 3 different ways. You know, if you were trying to integrate this 2 theta d theta, you would substitute this. This would be integration of sine u, and then the, sorry I'm doing this ahead, but sometimes it's useful. So how do we isolate d theta? Bring the d theta upstairs, bring the 2 downstairs. So we got d theta is 1/2 du. So there's a d theta. So we can throw in a 1/2 du. You know what I mean? Integrate that. The 1/2 pops out the integration, and we got cosine u du, which is just, you know, you don't have to use u as your, you don't have to use u as the u substitute. You can use anything, but I mean, now it's very synonymous with cosine theta d theta, which we can do. Okay, so how do we get there? Well, we have to know this is how I draw it. You know what I mean? So you have 2 angles, and they're the same. And this is your hypotenuse of 1. And so we can do a couple things with this. And maybe I'll try to blow it up. But this is like, if this is my hypotenuse, and I want to find the cosine component right here. So this cosine component, this would be the, like, this length is going to be the hypotenuse, 1, times the cosine of theta plus theta, which is 1 cosine 2 theta. All right. Now, if you don't know, like, do them both. You know what I mean? If you kind of forgot. All right, hell yeah. I mean, this comes from the perspective of, like, hey, maybe this is alpha and this is beta, and these are 2 different angles. But when these angles are the same, you know what I mean? It's just like there's only 2 things you could solve for. You know, if this is your hypotenuse, you could also solve for this sine component. You know what I mean? This length right here is going to be 1, your hypotenuse, sine of theta plus theta, or sine 2 theta. That's going to be that length. And then and then in this process, in the cosine process, you're going to get a cosine squared term and a sine squared term. But it is good to do these both. And so let's let's do them a little bit bigger and just a little bit cleaner. So I have kind of similar angles, theta and theta. I have to bring this out to some sort of point 1, and then we'll do these kind of simultaneously. So let's do the one that doesn't work. We'll do the sine component first. So if I'm trying to find this height right here, when doing the double angle, I always start with this hypotenuse I know. Like, I don't know anything about this triangle, but I do know this hypotenuse. And so I always start with the topmost line and the topmost angle. Okay? And then so I'm going to take the, and it doesn't really matter kind of which one maybe you take first, but I'm going to take, let's take the sine component, let's see. So if I take the sine component, but I'm kind of after maybe a length this way, and this is the only angle that's kind of tricky to see. Is like I have to know that this is theta. A couple ways to do that is to say that if this is a right triangle, if this is theta, this is phi. And I'm just going to say phi is 90 minus theta. So you could say this is theta, this is 90 minus theta, or just phi. So a right triangle will have theta and phi. If I know theta, I know phi, vice versa. Okay, so then what I can do, well, yeah, how do I get over here? Let's see how I would. Oh, right here. So here is a 180 degree line. So I know this is 90. No, that doesn't prove it. Damn it. This is gonna drive me nuts. Maybe come up here. Yeah, probably just continue these lines on. The other way to do it geometrically, I did a video on, like, let's say you rotate it. So let's say this 90 degrees is like a solid, like, you know, it's like a chunk of card. And then, so what I'm going to do is I'm going to take this chunk of card, and then I'm going to roll it down. So, okay, and then I'm going to compare this angle. So as I roll this up, hey, this angle becomes like a little bit. And so doesn't this angle become the same? You know what I mean? Because, like, let's say this angle goes to 90. It's just like, well, I don't know if that's even visually to see, but I think that is visually, you're able to see that. If I bring this up to theta, this angle right here with the vertical also becomes theta. And so I'm just going to leave it at that, because I don't know how you get the, like, how do you get, what's the other way to get that angle? Like, I'm kind of mind blocked right now. I'll think of it, though. Alright, hell yeah. So there's a few ways to get kind of similar, complementary, supplementary angles. Like one is kind of the Z shape, I think of Zorro, but hell yeah, I can get that. So this angle right here is theta, this angle right here is theta, and I'm going to continue that up, and then I'm going to notice that that theta plus, so this is 180 degrees, but I know that theta plus, so I just see that this is 90. And then I can do it mathematically, that theta plus phi is equal to 90. And so now I know that this 90 degree triangle, does that help me out? Damn it, I don't even know. Now, yeah, but at least we have that parallel line, and that's, you know, parallel to this line. And then we have this line right there. Holy Toledo, this is driving me crazy. Okay, so here's the other one. You know what I mean? If I have this, I also, this angle right there is also equal to that angle right there. Whew. You know what I mean? And then if, does that even help? Alright, I'm going to throw in the towel on that. I just really know that, yeah, if you move that up, I can see that. And that physical property happens a lot, especially in my like material mechanics book, is like definitely sweeping that angle and having that angle appear, and it's the same. So we're just going to move on. And we kind of just wrecked our drawing. So hell yeah. So this is my hypotenuse of 1, and we're going to take the sine component. I'm kind of interested in this vertical length. And so if this is my hypotenuse for the new triangle, so I'm going to say this is the angle, this is the hypotenuse, drop down to 90. And then so this length right here is going to be sine theta, cosine theta. sine theta, cosine theta. Cool. And then we took the sine component of this, so now we're going to take the cosine component of this, which is this length, and then we're going to take the sine component of that. So cosine theta is right there, and then sine theta. So this is cosine theta, sine theta. And that's that length right there. And then so this length plus this length equals what we were after at the beginning, the sine of 2 theta. Cool. So this was sine 2 theta, and these are the things that we add, but it's sine theta, cosine theta. What we are trying to get after is something that we're trying to get this. So this was a dead end. But I was just bringing this up because there's really only 2 ways to do. If your angles are the same, you could solve for the sine component, or you could solve for the cosine component. I guess you can solve for the tangent. I have never done that one. Don't really want to. All right, so we have this angle, and we're going to solve for this cosine component. And so what I do is just like, hey, same thing. Let's take the, let's take the first cosine component. So this is our hypotenuse. We're going to drop down a 90. We have a 90-degree triangle. This is the cosine component. Cool, let's take the cosine component again. And then this is my hypotenuse. Drop down the 90-degree angle. This is my new right triangle. This is the cosine component. So this was cosine theta, which was cosine theta squared. You're like, oh, okay, so now we're getting kind of somewhere. And it's kind of the definition of this, and so what this is 1 cosine 2 theta. That's what we're trying to find. We took the cosine, and we took this first component. It's too much length, so hopefully this next one we can kind of subtract. And so we're going to take the sine component of this. Same thing, I'm going to say that's the angle. And if this is my hypotenuse, I'm going to drop down a 90-degree triangle right here. And, I went too far on this. I really want to subtract this length to actually get what I was coming to get. And so this is sine. So we have the hypotenuse of 1. Here's the angle, sun shining. So this is sine theta. That's the length of that line if this is 1. Turn this into a hypotenuse, drop down to 90. Then I can take the sine component, which is that length. Hell yeah. So this is sine theta, sine theta. Again, this is sine theta, the first one. Turn it into the hypotenuse, and then take the sine theta of that. And so I should be pausing more on that. But here you have a hypotenuse of 1. If we take the sine of that angle, that's the percentage in this vertical direction of a right triangle, where the hypotenuse is 1, so that's that length. What we want to do is turn this into a hypotenuse. That's what we do by dropping down this 90, and then we have this right triangle. This is our new hypotenuse. We're going to take the sine theta of it. That's going to be the opposite component. That's the length of that component, and then, so sweet, so that is that length. And we just know that that first hypotenuse, so we have 1 sine theta, sine theta. That is the length of that. That length is sine squared theta. Sweet. So now we have this equation that says cosine 2 theta with hypotenuse of 1 is equal to cosine squared theta minus sine squared theta. All right. And then what do we need? We need cosine squared theta. And, it's like even red flags should go off right now. It's just like, well, if I solve this for cosine squared theta, it's like those little dolls where you like squeeze the eyeballs and it's just like, hey, don't I have more problems over here? You know what I mean? Now I'm just integrating this, cool, but I still have to integrate that as sine squared theta. Do I have to do this whole process over again? No, because now we can, we'll walk our way through it. We're going to turn this into a cosine squared theta plus something. Based on the identity. What do we say if we have sine squared theta? That's going to be the hypotenuse of 1 minus cosine squared theta. So we can just do that right now. Or like I think the way that you would do it is just like, ooh, cool, I have my cosine squared theta, so let's get that over here. Or just get this independently. So we have cosine theta is equal to cosine 2 theta, and then get this over there, plus sine squared theta. And then you're like, sweet. But if I sub that in, hell yeah, this integral, that part sucks. So let's play the game again. Not that game, but we just have to do this substitution, and it just works out. It might not seem like it does, but we're going to add 1 minus cosine squared theta. Cool. And so this becomes cosine squared theta is equal to cosine 2 theta plus 1 minus cosine 2 theta. So let's just get it over here. That's going to add cosine squared theta on this side. This was squared theta if I said something different. And then we have 2 of these, so that becomes 2 cosine squared theta is equal to cosine 2 theta plus 1. Typically, people write it like 1 plus cosine 2 theta, and we have 2 of them. We just want to substitute one of them, so we're going to solve this. So hell yeah, so we finally get, let's write this integral. So we have 2, well, we're probably going to get some new sheets of paper, but we have 2 r naught squared, theta is equal to 0, theta is equal to pi halves. And we're going to sub in, yeah, I should have solved this for cos. So we have cosine squared theta is equal to 1/2. I'm just dividing 2 over here, plus 1/2 cosine 2 theta. So now I can sub this into there. So we're going to have 1/2 plus 1/2 cosine 2 theta. Now, the elephant in the room is that when you know what I mean? It's good to be able to draw these every once in a while, because just the normal cosine graph, how we did it was just like, hey, just go 1, 2, 3. I'm going to go over 1, and it's fairly linear, and then maybe 1, 2, 3. Keep it linear, go this way. So we're gonna do something like that. But if we throw a 2 in here, it doubles everything. You know what I mean? We're only going to go to here and then start going linearly. And instead of going 2 blocks over, we're just going to go start here 1 block over. So I'm going to go down, and then down, and then so everything just got halved, and then so then I can I can do a full revolution of this in one go. Let's draw that one more time. Yeah, it's a good one to be able to draw. So we're going to go 1, 2, 3, 1, 2, 3. And we can even go farther. 1, 2, 3. And then finish it out. So cosine, flat, down, flat, down, flat, up, you know. And this is the small angle approximation, where you're just continuing that slope of 1, and it's a fairly good, and it really helps you draw this in, you know what I mean, because it's almost exact now, drawing this graph this way. So this is a very good way to draw cosine. What I'm saying is that if you have 2 theta, it just like, hey, your short section's only to there. Here the long section was down 2 over 2. So we're gonna be down 2 over 1. So that's where we're gonna hit. So I'm gonna come here, and then I'm gonna be down 2 over 1. So I'm gonna hit here, and then we're gonna go over a half. This is a half, and then we're gonna go over a half. Go up to here, go up to here, over a half, over a half, and then down to there. And I mean, but we already did. It's like from there to there was one period of the cosine graph. So this one, that is one period of the cosine. So that's what happens when you do this 2 theta. So this is cosine 2 theta. This is just cosine theta. And I guess I should have foreshadowed that, like, you know, if you do have cosine, this is 90, and then you have 180. Like what if you do the integral, and this is 0 to pi. What if you integrate this, the area under the curve? You have positive area, negative area, they're equal. So the integration of this from 0 to pi of cosine theta is just 0. 0 area, because these areas cancel out. So what we have is the integration of 0 to 90 degrees, or 0 to pi halves, of cosine 2 theta. So what happens is here's my 90, and hey, I get positive area, negative area, and these are going to cancel out. So that's the thing going forward, or the take-home point for if you're going to do this trigonomic identity. The fact that you get all the way through that, you get this 1/2, which just integrates to 1/2 theta, and then you input pi over 2. But this term, because we're going to be separating these this integral of both of these d theta. And yeah, so I sorry about that. I just substituted cosine squared theta, and then I got that substitution. But this d theta is still part of that integration. So there you go. And then when we integrate this, like literally, and you can break this up into two separate integrals. This one with 1/2 d theta, and then this one. And so yeah. So let's do that. All right, hell yeah. So I got that rewritten, and we got the two integrals, and we're going to integrate this. The constant comes out, whatever, but we're integrating from 0 to 90 of something that's going to cycle, and so the area is going to be 0. So if you can see that, you can just move on, and that's where this trigonomic identity to get. Now I see it, Like I was just saying, like, oh, you should do everything all the time, in the rigorous way. Or I guess I'm going to reframe that. You should do it rigorously if you're able to, until you're just like, yeah, it's kind of pointless. I've done that like 10 times. I've done it 100 times. I can move on now, and especially this one, because like, yeah, what a hassle to go through all that. This did become this equation. We used to get the 1/2, but the integrating of that just becomes 0. So this was the only important part of that, that whole identity of trying to figure out what cosine 2 theta is in terms of something else. Okay, but we can do a u substitution. So we're going to go u is equal to 2 theta. Okay, so we're going to do du d theta. And so always do this, and even do it a little bit more rigorously and say, hey, that's the equation. I'm going to change 2 theta. This is the equation of something. And, if the theta confuses you, treat it like y is equal to 2x. Okay, that's this equation. And what's the derivative of y is equal to 2x? So we're going to dy dx. Even when we do this, throw some parentheses on the y, and then throw that 2x in there. This is the easiest way to see how a constant of integration pops out, because this is just dx, and this is just 1, and you're just left with 2. Cool. But even, you'll probably skip this stage, but at least don't forget this stage. You're taking the derivative of u with respect to theta. And then you should do this, because you're just like, hey, if this was the equation, and you should probably get used to writing it as, like, hey, if this is my dependent variable, this is u, this is theta. When theta is 1, u is 2. When theta is 2, u is 4. So there's that equation. This equation is u is equal to 2 theta. Now, because like this is the first time I've ever done that, But that's very good to do, because now we can see what the derivative would say. The derivative would say, if I'm going to change theta like by 1, how much did the u change? Well, it changed by 2. I'm going to change the u another 1. And how much did the u change? It changed by 2. And you can only do this with linear ones, Else, if you do this with like a square root, you can't just go, you can't just hop one value and one value just because you're only getting an average change. That is going to be the average change. But that's the whole idea of you know what I mean. But with a linear line, the change here is the same as the change over a larger period. So anyway, cool. But yes, so if you do this all in one go, don't forget this. So we have du d theta, and then just take the derivative with respect to theta. It's just going to be 2. So if you see that, but just don't forget about this d theta. Like that's on the bottom. And now you do have an equation of 3 things. And then you're going to have to try to replace it with this d theta. That's the first thing. Just get d theta by itself. So d theta goes upstairs. The 2 goes downstairs. So it's going to be 1/2 du. And then and you really don't need to do anything more. You know what I mean? You don't have to be like, oh, I see a half there and I see a d theta there. You know what I mean? Well, it wouldn't be that way anyway, because you know I basically have a 2d theta is equal to du. That's what I have right here. That's also what this says, and I really don't have a 2. I just have a half. So just to make it less complicated, there you go. So there's what you're going to pop in for d theta. So yeah, so we're just going to be working on this one. So we have 2 r naught squared, theta is 0, theta is pi divided by 2. We have this half. I'm going to get rid of this half out here. We have so we have cosine u. So this was our u substitution. U is 2 theta. 2 theta is u. This d theta we have to replace with 1/2 du. And again, I could bring that puppy out, so I'd have another negative 1/2 over there. Yeah, let's write it again. So I'm going to have, this is going to be 1/4 times 2. So this is still just going to be 1/2 over here. So I have 1/2 r naught squared, 0 pi divided by 2. But again, it really doesn't matter because all this crap's going to turn into 0 anyway. So it's just kind of like, what a hassle to go through all this process. But it is good to do it the first 100 times. Okay, so now I have this. I have to integrate cosine theta cosine u du. The same thing as cosine theta d theta, whatever floats your boat. But what is this? So if I have the equation cosine theta, and the question is what equation? Well, let's just take sine theta. Sine theta goes like that. If I take the derivative of sine theta, what do I get? The derivative of sine theta is cosine theta, because here's the slope of 1. And then cosine is the slope of 1. The slope's always positive, so it's just positive cosine theta. And check it out, that's exactly what is right there. So I chose an equation, so that's kind of where the harder part about calculus is, like you have to kind of guess first, and then take the derivative and match it. And that's where I need to do a whole lot more integration by parts. I've never really done that, but I'm looking forward to doing that. Because, yeah, I don't know. Anyway, so hell yeah, so that's how you do it. It's the antiderivative. It's what equation, like sine theta, when you take the derivative of it, gives you the thing that you're trying to integrate. What that means is the integration of this is this equation. Because like I said, if you get that integration and you take the derivative of it, you're back to that base equation. When you integrate this, you get an equation. When you differentiate that equation that you got, you should come back to this base equation. The only catch is that the integration of this is going to be sine theta plus a constant. But when we evaluate it at both limits, you're going to have sine theta plus a constant minus sine theta plus a constant. And the constant goes away and whatever else. And obviously this is going to be sine theta at pi divided by 2, sine theta at 0. So let's walk our way through there. So we have 1/2 r naught squared, and now we're integrating this, and we get sine u. Limits of integration are going to be from pi divided by 2 to 0. And, you know, you could throw the constant in there. A lot of people don't. I don't think I'm going to, but I should. You know, I mean, it'd be my style to always have that in there. No reason you wouldn't. And then to actually explain graphically what that is. Because if I have y is equal to x right here, and I want the area under that curve, it's the same thing as this graph up here, where it's like a mile away. But I want the area just right there. The area there, and then you could think of that as your constant of integration. You have an equation that you can just vary, but you're still maybe just after that area. That's not fully representing, but that's the route that I would choose to go down. I would try to find a graphical way to represent how that C part just drops out, and you're just after, like, that area is going to be the same. Cool. Okay, so we're going to evaluate this. So we have sine, so we still have this constant out here. We can just do a big bracket, but we have sine pi divided by 2 minus sine 0. So sine of 90. Cool. Sine of, oh, damn it. Maybe I did make a mistake. This bummer. When, oh, yeah. My bad. So, yeah, I'm kind of new with this. Alright, so I just went through and explained the mistake that, you know what I mean, but I ran out of juice, so let's explain it again. So when I did the u substitution, my limits of integration changed. So I have d theta right here. That means that our limits of integration have to involve theta. So I have an equation with theta, a change in theta, and that's going to be from theta 0 to theta pi over 2. When I do this change to u substitution, I need to change my limits of integration. And so when theta is 0, 2 times 0, well, u is 0. Cool. And then when theta is pi over 2, so pi over 2 times 2, 2's cancel, and that's just pi. So I'm integrating cosine u du from 0 to pi. You know, I guess it's the same thing as cosine theta d theta, but hell yeah, theta would have to be 0, and theta up here would have to be pi. But yes, I guess, yep. So anyway, the limits of integration are from 0 to pi, and so that's what I changed. And so sine of pi is 180. And so we have sine of 180 minus sine of 0. And sine of 180 is 0, and sine of 0 is 0. And then let's even talk about that. Because what is sine anyway? Well, like if I have sine of 0, well, it's sine of an angle of 0. So let's draw a triangle with an angle of 0. Or 0 radians. So there's if this is where I start my angle, there's 0. Here's my triangle with the hypotenuse of 1. What's the sine component? You know what I mean? So that's going to be 0. So the sine component is 0. Then if I have a triangle, or the sine of 180. So if I have a triangle that actually starts 180 degrees, so we're going this way. This is the hypotenuse of 1. What's the sine component? You know what I mean? If the angle was 170, we would have that. This would be 1. And then the sine component would be, you know, basically that height would be the sine component. But in both of those, that's a graphical representation, visual, that the sine component right there, that height is 0. So we have sine 180 is 0, sine of 0 is 0. Sine of 0 degrees is 0. And yeah, that's the sine of 0 radians. This is the sine of pi radians. Pi radians is the same thing as 180. 0 minus 0 is 0, so even though it's multiplied by this constant, this whole term becomes 0. So that's why you should only do this about 10 or 20 times and then stop, and then just visually see that, oh, hell yeah, that's 0 by visual you know, representation, which we talked about with that graph. All right, so now we just have to focus. Now we just have to do that. Let's get a fresh sheet of paper. So we just need to do this integration. So we have I'm going to get this 1/2 out, so we just have r naught squared. Integrating, theta is equal to 0. Theta is equal to pi over 2 of d theta. When we integrate d theta, we get theta evaluated at pi over 2, 0 to pi over 2. We have r naught squared. And when we get this, we're going to have pi divided by 2 minus 0 multiplied by r naught squared. So we're going to have r naught squared, or just pi r naught squared, maybe like 1/2 pi r naught squared. So that is, and then, you know what I mean, now back to our actual picture of like what did, see that's the deal with getting kind of down the rabbit hole, is like, okay, so we took that horizontal line, which had an equation, and if we do this, you know, if we talk our way through it, this is the height of this line. That means that the y is my, in this case, my independent, no, y is my dependent variable. Z is my independent variable. And I get, yeah, so I have an equation of like, hey, y is equal to something something z. We give this little slice a dz, and we integrate from z is equal to 0 to z equals r squared. And then we get that area. So that, let me pull up the sheets. All right, hell yeah. So this is where we did that u substitution. We had this equation, and it was z. It was damn it, I don't know why I have a z there. If this is z right here, this equation should be y, so my bad. So we had a y equals equation, and we integrated, and then we gave it a little bit of dz, and then we did the integration of this, you know, y equals equation. So, and this is what I got to get better at. So what we did is we did the integration of y dz, and that, just the fact that this letter is different than that letter, that kind of messes me up. But in sense, this is the height. So we want that y equation where z is our independent variable, and so we get this equation that has z in it, and then we integrate. You know, we get this height, and then we're adding those slices. So that's cool. I guess. And then we saw that we can't integrate this easily, so we need to use those trig substitutions, and then it, you know, and then what was this integral? It was taking the height of that equation, giving it a little bit of width, and then adding those slices from here, from z is equal to 0 to z equals r. And so just about an hour ago, we changed those variables in terms of theta. You know, we turned all those variables. But in a sense, we got this, which is just the area. That's why you're only going to do this about 10 or 100 times before you're just never going to do that again. And you're just going to be like, cool, I have this equation, and I'm just going to, yeah, I've never even done it without the identity of just like, well, what's the area of this? Does that even make sense? Yeah, that this radius is r naught, and the area of a full circle with the radius of r naught is just pi r naught squared. So the area of that is just 1/2 pi r naught squared. You know what I mean? But I just don't think anyone's going to take you through the rigor every day. So so we did it, and we could do it with a vertical line. I'm going to do that with a separate video. You know what I mean? There's no reason to make 5-hour videos that only people watch 30 seconds of. But cool. So that is the area of this slice. And again, it's in terms of this radius, which back to the very beginning, which I don't even have the papers on, you know, but you can always do it again. It's like, hey, this is the hypotenuse, this is the radius, this is the height, which is the diameter, and this is the x value. You know what I mean? So this is the equation that we talked about, how you should just be able to, just pop it out all the time, is that if you're trying to find one of the sides of a right triangle and calling it an equation, so we're going to say y is equal to the square root of r. In this case, this is the full circle. This is a radius of r, and then r, I guess the negative r. So we have r squared minus x squared. Cool. So that's the diameter of these slices. We found the area of a slice. What am I even doing? Oh yeah, I'm just trying to show you what r naught is. So cool. So this is this function y is the diameter of that slice. If this r naught is the radius of that slice, this is the diameter, so I can say r naught is equal to y divided by 2. This is going to be 1/2, sorry, I'll write it better, 1/2 r squared minus x squared. Cool. So now we have this disk is going to be 1/2 pi, and it's going to be this squared. You know what I mean? So let's do that. We're going to have 1/2 square root r squared minus x squared, and we're going to square it. Cool. So that's what r naught was, and that's the area of that disk, and that's the area of that disk at every location of x. So we said, what if x is 0? Cool. This just becomes r squared, square root. That's r, and then we have r gets squared right there. This becomes 1/4. And so we have 1/4, 1/2. That's pi over 8. And that becomes pi over 8 r squared. So the area of this slice right there is pi over 8 r squared. Cool. And that's always a good sub thing to do. If I want to know the area of that little slice all the way at r, throw in an r here. R squared minus r squared, that becomes 0, and the area of that slice is 0. So hey, we got to check on reality there. So now this is the process where we're going to give this a little dx width. And so we're going to take this equation, which I don't even know what variable you would call it. But I think that's why in some books you would just call, like, hey, this is just the area in terms of x. Yeah, that's what they do in the videos. So it's just kind of fascinating, like, slow rolling these problems, because like I'm not very good at this. You know what I mean? I only do it a few times. I'm not. I think it takes like a lifetime of learning the technical rigor. I don't know. I have a hard time reading textbooks. I'd rather just do this process and then kind of spill in the technicalities as I go, as I have questions about them. But hell yeah, so that's what this equation represents. It's a as x. We gave it a little dx, and then that's our integral. And our x limits are negative r to r. Negative r to r. So hell yeah, so that's what that looks like from a technical perspective. And we are basically just about done with this video. So we are going to integrate from negative r to r this area, which is you know what I mean. I'm gonna write what r naught is, y over 2. That's going to be 1/2 r squared minus x squared, just so you have it. And then so this, if I sub this into here, this whole thing becomes a of x. And then so that's what we're integrating. So we're going to integrate 1/2 pi 1/2 square root r squared minus x squared. We're going to square that term because all this was r naught right there. And then we have a dx. Hell yeah. So this whole thing was the ax dx. So we have the area of that slice that can be anywhere from big to small, and we give it a little bit of dx width. We're going to add those slices. That's the integration sign, and that gives us that total volume. All right. we can do this squared thing first, you know what I mean? The square of this is the same thing as 1/2 squared, square root r squared minus x squared. These are fun things to do, I think. You know, even if you have a fraction, you're just like, what do I do? Well, this is just 1 squared divided by 2 squared. Cool, that's just going to be 1/4. This just gets rid of the square root, you know what I mean? And so let's get this 1/2 out. Let's get this pi out. This is going to be a 1/4. Let's get that out. We have integration negative r to r. This gets rid of that square root. So we have r squared minus x squared dx. I can separate this integral into 2 integrals, or I can kind of just know that and then do it all in one step. This is going to be pi divided by 8. When I integrate this with a dx, it's going to become r squared x evaluated at r negative r. When I do this one, we're going to have minus pi divided by 8. This is going to become 1/3 x cubed evaluated at r negative r. Cool. So this one is going to be pi over 8 r squared times r. That's going to be r cubed. And then we're going to have minus pi divided by 8. This is going to be r squared times negative r. I can do that. This is the same. I like to do this. Anytime I get a negative, that's the same thing as 1/2 times r. So this becomes r cubed. This negative makes this a positive. So basically I have pi 8s, r cubed. That's going to be 2 pi fourths. So this term right here becomes pi fourths r cubed. Hell yeah. Alright, hell yeah. My battery fried, but we're on the home stretch. So we're evaluating this at the limits of r negative r. And this is interesting because we have an r cubed. I'm going to do it up here and then we'll put it down here. So we, do you want to do this minus last? You know what I mean? That's where negative signs just drive me crazy. So, and even here, all this is just a big old constant. You know, you could just do that. And the only thing we're really evaluating is this. You know, so that kind of keeps it simple. We got r cubed minus, we have negative r cubed. So, but we do have this, even right here, this is good to write as negative r, negative r, negative r. And even how you could write it, again, I said this is negative 1r, negative 1r, negative 1r. You know what I mean? So this is r cubed, and then you have 3 negatives. So only one of them, these two are going to make a positive. You're only going to have one of those negatives. So after all of that, negative r cubed is going to be just negative r cubed. And then we have this negative sign right there. So that's going to be plus r cubed. And so we're going to have r cubed plus r cubed. So this becomes 2r cubed. So that's that evaluated. You know what I mean? And then multiplied by this constant and the negative. So now we can bring back that negative, pi divided by 8, 1/3, and then we have 2r cubed. That's going to be pi divided by 4, and this is going to be minus pi 12ths r cubed. So this term is going to be pi divided by 4, and we're going to subtract pi divided by 12ths r cubed. I'm going to multiply top and bottom by 3. So this is going to be, 3/12. So 3/12 minus 1/12. Cool, so we're going to have 2/12, which is 1/6. So we're going to have 1/6, or pi r cubed divided by 6. And booyah. So that's the answer. You know what I mean? That's the volume of that shape. So we have this shape, and if we if we find the volume of that shape all the way from r to negative r, the volume of that shape is going to be pi r cubed divided by 6. So whatever, you can then set your limits however you want your r to be. But booyah. So that's that. And I'm done with this problem. And so, man, I don't know. Yeah, this was either the worst or one of the best videos on integration on YouTube. So I think that's how I'm going to title this video. But hell yeah. I mean, I enjoy doing it, but right to a limit. I mean, obviously I'm probably bad at... What I just see on YouTube is not a lot of people doing stuff like this. But, it's not going to rise to the top. A lot of people just do very quick stuff. If you can go over a topic in 2 minutes, but like something like this had about 100 different topics in it. You know what I mean? So it could be like 100 different videos in the course of 3 to 4 hours, however long this video is. So it's not bad in regard to that. But yeah, I mean, my methods are repetitive, but I think it's helpful. And I'm always going to put red flags. Anytime I say something and I'm just like, that didn't really make much sense. But even right at the end there, I never got where, these symbols came from, where you had this area in terms of x. But then along the way when we were integrating, it was like, hell yeah, I was saying that this is a line that has an equation. For this one, it's y in terms of z. And then we're integrating that. So now I see that, hey, once we got that area, that disk, it becomes this area function, and we're integrating. And it has a variable, and we're giving that disk a little bit of width, and then we're adding all those slices up in that direction. So, all right, booyah. So thanks for joining me on this one, and that's a video.